Welcome to what I hope may very well become the definitive course for learning Grasshopper. I've created this to make the most comprehensive, succinct, engaging, fun, and achievable course that there is on Grasshopper because I think that it is a phenomenal design tool and people usually find it extremely overwhelming to learn. So this course will take you through step by step from absolute basics to an extremely sophisticated understanding of everything that is inside of Grasshopper and then how to use it.
We'll begin with an overview of the interface and how to create basic geometry types through an exercise that highlights the benefits of Grasshopper compared to manually modeling things in Rhino. After this, I'll guide you through a full modeling exercise where you'll be introduced to a comprehensive suite of modeling tools. Working through this exercise will simultaneously develop beneficial scripting habits like grouping, color coding, labeling, and using nodes to keep your scripts clean and legible. You'll then learn how to use custom material displays and color gradients, after which I'll show you how you can use camera controls to create animations. Once you've learned all the tools, modeling workflows, and display techniques, I'm going to guide you through the tricky concept of data structures in the simplest, most easily digestible way that I possibly can, because this is always neglected by students, but it's what differentiates intermediate from advanced designers. Finally, we'll conclude with a few additional short workflows that I thought could be valuable, such as how to efficiently diagnose why a script might be crashing, how to troubleshoot common modeling issues like repairing broken meshes, and then quickly touching on how you can integrate machine learning to optimize your designs before we finish by pointing you in the direction of what you might like to learn next. So things like coding your own plugins in Python or C#.
Now this tutorial comprehensively covers everything that you need to know about Grasshopper, and by the end I promise that you will thoroughly understand how the software actually works and how to use it properly. Once you've got that understanding, the next question is what can you actually design with this exceedingly powerful creative tool? So for anyone that wants to keep learning, I've put together what I now feel confident in saying is the most comprehensive and advanced library of parametric design, but in particular, fabrication resources that are available anywhere in the world right now to help you to continue to progress your skills and pick up an extensive range of design workflows. You'll find the full course library linked below, and you'll see that there is a massive range of tutorials and really advanced resources for you to explore. The beautiful part of how I've set this up is that for each of these designs, you can download a Grasshopper script that I've written and watch a detailed but concise tutorial that explains what each script does, how each part of the script works, and then takes you through in detail, step by step, how you can apply it to your own designs. So it actually lets you design your own shape, whether that's a sub-D, NURB, surface, polysurface, or mesh in Rhino, and then reference your own design into this script and it will instantly panelize it for you. Each script is meticulously grouped and labeled so that you can easily interpret how it works and what each parameter adjusts. The scripts are basically self-explanatory, so you don't need to watch the tutorial if you don't want to, but if you do need it, then each script has a detailed video tutorial lesson crafted with the same level of care as the video tutorial that you're watching right now. There are a huge range of systems that you can apply, from timber frames to spiked protrusions, glazed spaced frames, timber grid shells, deformed building skins, field simulations, coral biopanels, voxelizations like this, which actually let you break down the overall building that you've designed into boxes or voxels, and it lets you design a reference shape, in this case a Kengo Kuma style timber panel, and it morphs them to fill each of these reference building shapes. There are so many designs for you to explore. I know that this almost feels like cheating in architecture school because you can spend 5 minutes designing a very simple shape in Rhino and then apply my scripts, and it makes it look like you've done a lot more work than you've actually done. But the point of this is to make Grasshopper as accessible and as satisfying to learn as possible. Grasshopper has traditionally been an exceedingly difficult and prohibitively overwhelming design tool for most people to learn. So this is intended to make learning feel as effortless as possible. Hopefully you'll pick up the logic behind these components without even noticing. Now, this next part is what I'm actually most proud of. This course's library also includes a large set of fabrication resources that automate industry-leading parametric fabrication workflows. You might not necessarily understand why this is such a big deal yet, but as you progress in this industry, you'll find that most parametric learning resources like forums or YouTube videos or design courses typically only ever explain the fundamentals like basic components, or it might explain a single plugin, but virtually no one actually shares the advanced proprietary systems that are used to build parametrically designed buildings, because obviously it represents the intellectual property of hyper-competitive design firms and university research departments. So typically, the only way to learn these skills was to build these systems yourself by spending years piecing together information from thousands of forum pages and experimenting with different plugins and then getting guidance from professors and colleagues and so on. But I think that it's in everyone's best interest for there to be a place where designers can actually learn these skills really accessibly. So as you explore the course offerings, you'll see that there's a range of extremely advanced but super user-friendly Grasshopper scripts that I've personally built from the ground up for you to learn advanced industry-leading fabrication workflows. Each fabrication methodology has a script that you can download, which is grouped, labeled, and annotated. Plus, there are detailed tutorials that explain what the design system is, how to use it, how to apply your own geometries, how to generate fabrication files, and then how to assemble each model in a variety of ways. It allows you to complete the entire fabrication process for your buildings within seconds. So to use the scripts themselves, you just need to reference whatever shape that you want from Rhino, and it will automatically rationalize the panels by running simulations that planarize them or flatten them. And then it will add flaps or tabs or slots depending on what systems that you've actually referenced. So in this perforated quad model, for example, what the script will automatically do is break it up into panels. You can reference how many panels that you actually want. And then for each of these panels, it will take it and it will lay it out flat onto a bed. And then it will add flaps to each of these panels like this, where you can bend them, and then you can glue these panels together. And you'll see that it actually builds up an extremely rigid model like this that conforms to whatever shape that you've actually created, which is the same workflow that you'll actually see out in industry to construct really advanced parametric buildings. And just to be clear, the script automates the process of taking these panels and laying them out flat, and then actually nesting these together onto sheets so that they're arranged as efficiently as possible. Finally, it'll add all of the correct labels so that you can easily assemble it together. And each script also features an inbuilt assembly guide that will help you to actually assemble these models. So to see how this works in action, take for example this contour terrain model. What the script will automatically do is slice it up based at whatever layer height that you reference, depending on what, I suppose, material that you're actually using. And then it will create all of these individual panels like this from your shape that you've referenced in. And you'll see that each panel contains two distinct features. So firstly, each panel has got a label for what the panel number actually is. This panel is panel number 11. The second thing that this script has got is that it has all of these dotted lines which show you how you actually assemble these panels together. So you get precise placement and it builds up an extremely clean model like this, and it makes the process of actually assembling it together really, really easy and really satisfying and really, really efficient. Another script that's featured is this waffle model, and what this will do is slice up the panel at intervals that you reference in, and then it will add all of these slots automatically to each of these panels so that it fits together really seamlessly and easily. And then it'll also label each of these panels. So this panel is Y10, and the panels that go in this direction will be labeled as Y, and the panels that go in this direction are labeled as X panels. And then you can just use the fabrication guide to assemble it together really, really easily. There are a huge range of different scripts for you to explore. So this, for example, is the grid shell model. And what this will do is that it'll slice your model up into a range of different strips. And each of these strips will have labels going the X or the Y direction and have a numerical individual strip number. And what you're going to be able to do is reference where each of these individual intersections are between the panels, and you can stick them together. It's a bit more difficult and tedious to assemble, but it ends up creating really, really impressive and really elegant models. And these scripts contain some really smart features. So in this terrain model, for example, all of the labels are hidden and it creates a really clean model like this. And the way that this is done is that it puts all of the individual labels underneath the overlapping panels as you stick them together. But for each of these top panels here, it will actually have the labels on the base so that you can flip all of these top caps over like this, and you won't see the label number. And there are plenty of other clever little features built into this too. So for example, you can see that this model is totally hollow on the inside. You can actually control how far each of these panels are offset inwards to reduce the material use and make the models much lighter while still keeping it super rigid. And as I was saying, every single one of the scripts contains a built-in fabrication guide that shows the assembly order of the panels and allows you to highlight each panel individually to simplify the assembly of the models. Why I'm so proud of this is because each exercise distills down the really advanced skills that you need if you want to be ambitious in practice to take advanced designs that you create and actually build them in the real world. But it does so in a really efficient, fun, and accessible way. The fundamentals of planarization, rationalizing panels, nesting them onto sheets, labeling connections, and providing assembly instructions are how really advanced architectural structures are built in real life. Each of these model making exercises is a way for you to learn the entire process of turning shapes into panels and then rationalizing those panels into something that can be built, creating fabrication files, and then assembling them together. These are very rare skills in the industry, and it will give you the opportunity to go out and design and innovate at the highest level. The other thing that I've been really conscious of is that obviously not everyone has access to resources like laser cutters. So each of these systems can be fabricating by printing the panels on standard pieces of paper as well. So you can see here that this space frame model that's featured just over here can actually be printed out using standard pieces of paper from a normal color printer. Or in this model over here, for example, we can actually print out individual strips that then can be connected together by either gluing the panels or by using sticky tape like what I've created here. And what you'll see is that they actually really efficiently conform to non-uniform shapes, like really advanced shapes like what you've got here. And it assembles together to create really impressive models that show a proof of concept for advanced construction methodologies. But if you do happen to be studying at SciArc or Milan Polytechnic or the Graduate School of Design or Peking or wherever that gives you access to laser cutters, then you can start to assemble some really impressive models like this. This was actually created with acrylic panels that have their panel numbers and also the connections and also the member sizes etched onto each piece of acrylic. But just to be clear, you could also create this model even with just the paper cutouts if you wanted to, and then some lightweight balsa. They're actually very cost effective to assemble all of these models together, regardless of whether you make it out of laser cut materials or if you wanted to print out the individual panels on a color printer. And these fabrication methods would look incredibly impressive in your portfolio. If you are aiming for a top university or job position, it typically takes less than a day to fabricate and then assemble all of these models, and it enormously differentiates your level of capability. There are very few people in the industry that have this level of advanced design skill. Even if you're working in practice, think about how quickly building a terrain model and then 3D printing a house on it shows a level of care and capability and lets you stand out. It also lets clients walk away with a small tangible model of their home, something that they can actually hold and understand, that's really easy and inexpensive and very time efficient for you to actually put together. So if you're interested, there's a link to the full course and resources library in the description below. I want all the work that I put into this to be as accessible and impactful to the industry as possible. So there are two ways to gain full access to everything. You can either get monthly access, which at the moment is less than $10, which is like unbelievably cheap for what it offers, especially when you take into consideration the costs and the time that this will save you. If you want, there's also an option to gain lifetime access to the library for $99 so that you can use these scripts throughout your time at university and draw on them when you're actually working in industry. And this support obviously goes towards my costs of licenses and equipment and materials to do the research that I want to do to provide you even more resources. It's been incredibly humbling that 250 people have already signed up to the platform so far. The most popular tier has been that lifetime access, and with this I will make sure that you've got access to all of the updates that I happen to add in the future as my way of saying a big thank you for supporting this in its early stages. I have massive plans for building up these resources, extending well past Grasshopper, things that I promise you that no one else in the industry is even close to offering, and I'm aspiring to make this into such a valuable resource for designers if it gets the support that it really needs. $10 to $100 memberships hardly cover the expenses required to put these courses together at the moment, so unfortunately it's likely that this is only temporary while I'm getting everything up and running, so Genuinely, I am deeply sorry if you're watching this down the track and prices have gone up. They're really only sustainable while I'm getting the course up and running, but I want this to be as accessible as possible, so I will do my best to honour our values of accessibility, but it takes a lot of resources to do the research and testing that's required for these videos. Regardless, I'll try to maintain it to be as accessible as possible. Even if you don't plan to purchase any of the courses, I really encourage you to have a look through what these courses cover and the kinds of designs that you can actually make in Grasshopper with it to give you a bit of future direction. So things like panelization and field simulations and contouring and box morphing and everything else that's included in the library. It'll give you ideas of what is actually possible in Grasshopper. And then maybe next time that you're struggling to meet a deadline, you can remember back to these scripts, download one, and you'll be able to turn around a lot of extremely impressive work very, very quickly. If you don't think that this is useful at all, please also let me know in the comments too. I genuinely really appreciate both positive and negative feedback to help keep improving and making this genuinely helpful for everyone. If this continues to be successful, I plan on massively building up the library because I would love to make resources that show how to render these designs out with a range of industry-leading render software and make a course that's as comprehensive as this one about compositing these images inside of Photoshop to the quality of some of the renders that you'll see on the website. It will also help us expand above just offering courses into hopefully being the industry-leading design firm that I aspire for it to one day be. So I really hope that this proves to be a valuable resource for each of you. It's obviously been a massive undertaking of time and effort for me to get it to this point, but it's something that I'm really proud of and hope can contribute to the industry in an overwhelmingly positive and supportive way. So let me know if you have any feedback in the comments below.
You can also find the link to the full course's website there. Now, before we get started, I've just got one more project that I want to share with you.
Over the last year, I've actually been designing, prototyping, and then subsequently streamlining the mass production, packaging, fulfillment, and order processing for my own product range of these highly intricate pencil and tool cases for designers, which I'm incredibly proud and excited to announce. They come in 3 sizes, as you can see here. These compact cases carry 20 pencils or pens, and they've been designed to fit discreetly into your bag so that you can carry them to school or university or work. These 36 pencil cases are slightly larger, but they're still quite portable. They're more intended to be something that you carry in like a tote bag if you wanted to go and draw at a park or a beach, or just spend time drawing anywhere that you really want to that's not home. And then these 52 pencil cases, which have 2 levels of storage space, are less portable, but they're designed to store heaps more stationery within it. And so you can leave this in your room or your office or wherever you need it, and then store all of your stationery and all of your drawing tools or any of your creative tools inside of it. Currently, they each come in a range of colors from green, blue, red, orange, and yellow, and they're unlocked through this smooth, precise mechanical procedure, which I've engineered and tested through dozens of iterations down to the nearest 0.1 millimeter tolerance, so that it feels as satisfying as possible. So listen to this. And this unlocks the lid mechanism on each of these different cases. And every design choice has been made so that these can endure as a lasting design tool. So to get a little bit technical, they've been printed in PETG rather than PLA so that they've got the highest UV, moisture, and heat resistance. The screws that hold it together are 304 stainless steel, and the sliders and cogs are printed with 100% infill and orientated so that they're not weak along the layer lines. The assembly of the parts has been segmented so that each part braces itself so that it's as stiff as possible, and the cases have been designed to be as robust as possible so that if you drop them, they stand the highest possible chance of not breaking any of the intricate mechanisms that are inside it. I've not allowed for any compromises on the design, fabrication, or assembly on this, and I've built them to last because this is what Legacy Design Studio was meant to be all about. It's meant to be about exceptional, enduring design. And just to be clear, this is entirely me right now. So I've designed these, I fabricated these personally in a back room in my office. I assemble them at my desk after hours when I feel like a really low bandwidth task, and I even apply the graphics to the packagings myself. The smaller boxes are actually recycled packaging from the delivery of 3D printed spools, and the larger boxes currently have their graphics plotted at the edge of my desk after everyone's gone home for the night and it's getting late, so it's okay to make some noise. So if you want to help support Legacy Design Studio's learning resources, or ideally if you just resonate with this as a design tool that excites you or that you'd be excited to gift as a present to a friend with a passion for design one day, then considering one through the link in the description below to our Legacy Design Studio product page. Okay, I've got one more project that I want to share, which is that I'm about to launch a video series on the professional journey of building Legacy Design Studio as a creative practice, because I think that it'd be really insightful for a lot of designers to see a raw, honest look at the experience of founding a design practice and developing product offerings. But also I want to touch on what's professionally led up to this point to help guide people out there that might be interested in the design profession but don't necessarily understand the context of it, or might not necessarily have a lot of direction in it as of yet. It's something that I hope can be really interesting, but also expose a behind the scenes look at the design industry itself in a way that no one's really authentically talking about it. This isn't something that I want to share entirely publicly, but I would love to share it with a like-minded community that maybe resonates and is passionate about these topics. So it's something that I'm going to post as a video series on Patreon. You can go check it out if you're interested. There's a link in the description. Okay, so before we get started, I want to show you what Grasshopper is and how it differs from basically every other geometric modeling software that's out there, and exactly how it's able to model such incomparably complex, intricate, and expressive designs. Unlike manual modeling tools, where you need to either like extrude or scale or rotate things individually, the way that you model inside of Grasshopper is through what's referred to as relationships or algorithms. So to give you an example, have a look on screen.
And what I've done is set up a rectangular grid of points on this red surface, which looks like this. Then, at each of the points on this grid, I'm going to generate a circle like this. Next, what I'm going to do is set up what's referred to as a parametric relationship between the size of the sphere and how far each sphere is from the curve that I've referenced in. You'll see that as I adjust the curve in Rhino, that it actually affects a variation of each of these circles. This ability to vary the design of things en masse is what makes Grasshopper so powerful as a design tool, because it's just as much effort to create 4 spheres as it is to create 40,000 spheres.
So what we mean by a parametric relationship is that we're designing elements according to a given variable. So for example,
in the Albeha Tower, we can see that there's a relationship between the path of the sun throughout the day and the opening and closing of the origami-style facade panels to reduce solar loads on the building. Or in Zaha Hadid's Haydar Al Aviv Center, we can see that the frame isn't designed manually. The dimensions for each panel of the frame is parametrically reactive to the curvature of the overall shape of the building. In the Elbphilharmonie Hamburg by Herzog de Meuron, we can see that the interior panels are all unique, and that Grasshopper is used to schedule the documentation of these panels. Or in these incredible pavilions by the very many, a sophisticated rationalization script has been developed to panelize any shape that they reference in, meaning that they can apply this script to any pavilion shape that they want, and the documentation and fabrication files could be developed automatically for each strip pretty much instantly.
The only prerequisite that there is for this course is that you need to have a good understanding of Rhino. If you don't, consider checking out the course's website, where you'll find a complete and comprehensive course on Rhino that takes you from absolute basics through to the most advanced tools that there are in a single 2.5-hour tutorial. Okay, so let's get into the Grasshopper course. Firstly, as you watch through this tutorial, it is extremely important that you actually have Grasshopper open on your computer and that you do each step yourself exactly the same way that I do it. Believe me, after teaching hundreds and hundreds of students Grasshopper, you simply will not retain the information and the knowledge if you just watch it on your phone and you don't actually follow through with it yourself. You'll lose concentration, you will miss crucial pieces of information. So just do yourself a favor and set up this tutorial on another monitor or another computer or an iPad, or even have it running on your phone. So just follow along and do it all yourself, copy through step by step.
Okay, so let's get started in Rhino. So to start Grasshopper, we've got 2 ways of doing it, in the same way as we've got 2 ways of running any command inside of Rhino. Firstly, this icon here is the Grasshopper icon, so you can click it to launch Grasshopper, or you can go to the Rhino command bar up the top and type in Grasshopper, and you'll see that this window pops up that starts loading all of, I suppose, the Grasshopper plugin itself and all of the plugins that are associated with it. This will give you a little bit of an overview of all of these different components if you wanted to go through some tutorials. Explore it if you want to. As soon as it's loaded up, this is the overall interface that you will be greeted with. It's really similar, I suppose, to the Rhino interface itself, in that you've got all of these menus that run across the top. I know that you won't have all of these different options at the moment, but I'm going to show you how to install plugins a little bit later on. But you'll have all of these ones to the left-hand side. When I took you through how to use Rhino itself, I was showing you that it's great to actually go through these different windows to learn what each of the different components are. So under the selection components, you could sort of hover over all of this and learn what each one actually is. In the same way, if we go back to Grasshopper, you could go to all of these different things. So if you wanted to learn what all of the different surface components are, you can have a look through here under surface analysis. And this is how we analyze surfaces, or this is how we create primitives. So if we wanted to create a box, we could create it from the center or using 2 points, or cylinders or cones, whatever it might be. Or same with like meshes, we can do mesh analysis, or we could create mesh spheres or mesh planes or mesh boxes. And this is a really good way of actually going through and learning what is actually available inside of Grasshopper itself. So you've got 2 ways of putting in different Grasshopper components. The first one is that you can actually click on any of these different windows and then choosing a component and bring it in. So if we choose our point component here and we click on it, then what we're able to do is we can drag it into this canvas. And when we click again, it'll actually place it inside the canvas itself. The other thing that we can do to bring in components is that we can double click on the canvas itself. So if I double click now, I'll be prompted with this search bar. So it says enter a search keyword. So if I wanted to, I could type in point like this, and then I would be able to select this point component. It makes it very fast to actually enter in a lot of commands very, very quickly. Now, one thing that I'll get you to notice is that see how my component here says point with all of the letters? Yours probably just says PT at the moment. And so what I want to introduce you to is that there are different display settings. If we go up the top here where it says display, and one of the main ones is that you can say draw full names. You'll see that by default yours probably looks like this, but I've got draw full names turned on. This is really helpful when you actually start learning what these components are. So if I was to, for example, go to surface tools and maybe I create a center box like this, which is just a box, it'll actually give the full name here, like base and then center box. Whereas if I had draw full names turned off, it is a lot more compact, which is really, really useful once you know all your components, because it makes the script much more efficiently compact. But for the time being, and for the purpose of this tutorial, let's turn draw full names on so that you've got all of the full names turning up and it's easier to learn. There's also an option here called draw icons, in which case it will actually give you the icons of what each of these are. It's up to you if you want to use it. Personally, I prefer just having names displayed so that it's actually easier to search on Google if you don't know what it is. I will say that basically all of the commands inside of Rhino are actually pretty much exactly the same as the commands inside of Grasshopper, aside from a couple. So if you wanted to scale something or rotate it, or if you wanted to extrude something, all of those commands are inside of Grasshopper itself. They share the same command system. So it makes it really easy for you to learn, but there are a few key differences. So say for example, planar surface. So planar surface like that, which lets you create surfaces out of flat curves, is not called planar surface inside of Grasshopper itself. You'll see that there's no command there for planar surface. What I would suggest if you come across this problem, I would suggest that you've got 2 ways of dealing with this. Firstly, you can go into Google and there are some sensational forums online. So Rhino 3D, where it says how to make planar surface in Grasshopper, or particularly the Grasshopper 3D forums as well, are really, really well populated. A lot of the posts are quite old, but they're still just as relevant as before. The other thing that you can do, and again, I'd say this is like a second option because it's really important to be, involved in these communities and give back as well if you can in the future. But the other option that you have is that ChatGPT is in fact trained on, I suppose, all of the Grasshopper forums. So if I'm asking I want to use the planar surface command for Rhino, but I can't seem to find it in Grasshopper. What command can I use? Then it's actually really, really useful to give you advice on how to do things for like small commands. Now, the next thing that I want to do is I want to show you how to install some of these extra plugins.
As an insight, what makes Grasshopper so powerful as a software is the incredible community of people that have actually developed all of these specialized plugins that you can actually use inside of Grasshopper for free. They're coded and shared by individuals and also, I suppose, practices and researchers and university professors and hobbyists and a whole bunch of other people. And they actually create their own tools, like they code up their own programs, which you can then plug into Grasshopper for very specialized purposes.
So what we could do is that we could go into Google itself and say food for Rhino. And it'll take us to this website here. And here is where you'll find almost all of the plugins that you can install inside of Grasshopper. There are some that exist outside of this. I think maybe Weaverbird perhaps. But almost everything else is inside of Food for Rhino. So if you search for a particular plugin, so let's say Aurora, which has come out very, very recently, this one down here. So the point of these plugins is to extend the capability of Rhino and Grasshopper itself. If you learn how to code in Python or C#, you can actually write your own custom programming like this. This plugin, Aurora, was actually developed by my mentor, Mark Gibson, who's a full-time researcher at the uni that I work at, and he is insanely talented. So he actually developed this to allow people to create brushable behaviors that autonomously grow and adjust and refine a mesh like this in real time, which is a totally radical way of modeling from how you would traditionally model in Rhino or Grasshopper, and is more similar to the sculpting tools that you'd see in programs like ZBrush. There's a whole lot of plugins that I think that you should just generally be aware of. So things like Lunchbox and Ngon can help with panelization. Karumba does structural engineering calculations. Ladybug does thermal analysis on your buildings. Kangaroo does physics simulations. So you can see here in these images that it creates structures by actually simulating each of the members as springs. I actually use this in heaps of the different fabrication scripts that I talked about earlier to OpenNest automatically nests panels for fabrication. Human extends Grasshopper's ability to create and reference geometry attributes. And Pufferfish and Weaverbird are really useful tools for mesh modifications. We'll actually use this one in this tutorial because we can utilize it to round off the edges of a bunch of different meshes with some of their different smoothing tools. Okay, so if we go back to Aurora, I'll show you the traditional way to install all of these plugins. What you can do is that you just go down to the download section of this and you're able to log in. You'll need to make an account if you're doing this for the first time, and then we can click on download. And you'll see that it will actually start to download this plugin. Now, the next thing that we need to do is that we need to go to our downloads folder. And inside this download folder, you'll see that it will be downloaded as a zip file. Now, there's something that is extremely important that you need to do, or else your plugins will not install properly on Windows. But this isn't something that you need to do if you're following on Mac. What you need to do is right-click on this zip file, and then go to Properties. And now you'll see that down the bottom right, there's a box that says Unblock. You need to tick this, and then click OK. If unblock isn't an option, then you don't need to worry about this. Sometimes it happens, sometimes it doesn't. It's just an annoying byproduct of Windows antivirus protocols. I just want to be very clear at this point that if you go to use this plugin and it doesn't work, or if it's missing inside of Grasshopper, you most likely haven't followed this step properly. So just come back to this point in the tutorial and follow this step and make sure that you're following it exactly. Okay, after you've been extremely careful to make sure that this zip file is unblocked, what we're going to do next is we can right click and say extract all. If you're running on Mac, you just double click on this and you don't need to worry about the unblock function. And so now it's extracted this zip file here, and you'll see that there are a few different components. So there's this green one here, and then there are a whole bunch of DLL files as well, which help these components to actually run, or help these plugins to actually run. There's another important step that's involved in this, which is if we right click and go to properties, just make sure that it doesn't say blocked on here. The reason I got you to unblock it when it was a zip file is because sometimes this helps to keep these unblocked individually, and it saves you a lot of time and effort. Because what we need to do is we need to copy this in to a different folder location, which I'll show you in a second. So to do this, we can go back to Grasshopper, and we're going to go File, Special Folders, and then Components folder. And this is where we're going to put all of our plugins. You can see that I've already got a lot of these installed down here. And what we're going to do is that we're going to take this green file, and we're also going to take all of these DLL files, and I want you to drag them across directly into this libraries folder. If some of them say replace files in destination, you can skip these because potentially where it says like Plankton DLL, that might already happen to be there for me, so you don't necessarily need to worry about it. And then once you've dragged this over and installed all of these plugins, what you just need to do is close Grasshopper and then close Rhino itself, and then we'll reopen it again. Once you've closed down Rhino and then reopened it again, all of the plugins components will be there, and you'll be able to use them hopefully. If they haven't turned up here, then what you should test out first is right click here and then go to properties and just double check that all of these are actually unblocked. If they're not unblocked, just click on unblock and then say apply or okay. And unfortunately you can't do this to multiple at once. You need to do it individually. It's a massive pain in the ass sometimes, but it's a necessity. There are quite a few plugins that I'm going to cover in this tutorial which will dramatically elevate your capability in Grasshopper. So here is a full list of what you need to install before you follow through this tutorial. Now, you can either download these from Food for Rhino one by one, and I do really encourage you to explore that website. But to make learning Grasshopper more accessible and easier, I've also created a file that you can download all of these plugins all at once. Just to be clear, this is a totally free download. It wouldn't be right for me to put this behind a paywall with all of the work that the community puts in to make them available to you. I have looked through the terms of service on Food for Rhino, and there doesn't seem to be anything limiting me redistributing them like this. And overall, it's just to make learning Grasshopper easier. And I hope as well that the creators want more people to use these tools that they put so much passion into. So if you follow the link in the description below, it'll take you to this courses page, and we just need to scroll down, because down the bottom here, we've got all of our free resources. So this is for the Grasshopper tutorial that we're watching at the moment. And you can see that under the Grasshopper tutorial, it says free access to plugins. So we just want to click this link, and this will take you to the free courses page. So you can see you've got like the free Rhino course, and you can download the resources for that here as well. But we want this one, the free Grasshopper course resources. So we can just click down and then click start. And then you'll see down here that it says free download Grasshopper plugins for legacy scripts. So you can just click download here, and it'll download that file for you. There's also an installation guide, which is basically the same guide as what we've just gone through. And then what we're going to do is go back to Grasshopper, and we'll go File, and then Special Folders, and then Components folder. And we're going to take all of our scripts here. So we'll select all of them, and we'll drag them across into our libraries folder. And then you just need to close down Rhino again, and then reopen it. And then all of these components should be installed. Now, there's one other plugin that I want you to install, and it installs in a slightly different way. This plugin's called Weaverbird. It's for mesh editing. So what we're going to do is type in download Weaverbird, and then go to this website here. And you'll see that on this web page it says here, download Weaverbird for Rhino 6, 7, and 8. So we'll just click on this link, and it should let us save where we're going to download this to. And then we'll go back to Grasshopper and then back to our downloads folder, and you'll see that you will have just downloaded this blue Grasshopper file, and we're just going to copy this onto the canvas inside of Grasshopper itself like this, and it'll come up saying unrecognized objects like this. And so what we'll click on is say download and install, and what this does is that it uses the package manager that's built inside of Rhino to just install all of this stuff automatically. So it says here successfully installed the missing plugins. And so we can close this now, and you'll see that all of these plugins will now run. And so now you should have all of the different plugins along the top here, and we'll also have Weaverbird installed here, which is excellent. If you have any issues with this, just make sure that you go back to your file and then special folders and then components folder, and make sure that these are unblocked. So go properties and then check whether everything's unblocked, because that's where 99% of the problems in installing this come from. Okay, so let's get started inside of Grasshopper now. Just to reiterate, all of the menus are up the top along there that I've introduced you to with already, and we can double click to search for things like points. Now, inside of Grasshopper, there are two ways to start working with geometry. Firstly, is that we can actually work with geometry that we've referenced. So if, for example, we take this surface here, like so, and we build it out like this, and I'll set my viewport to shaded so that we can see it a little bit better. What we can actually do here is that we can go to these different geometry types, and we could select our surface geometry, which is just here. Alternatively, you could type in surface, and you could use this part here. What we can do now is that we can right click on this component, and then we can say set one surface or set multiple surfaces if we wanted to set multiple, and then it'll prompt us inside of Rhino itself what surface we want to reference. So if we select this one, then now you can see that this surface is actually referenced inside of our Rhino window itself. And if we wanted to, we could use any of those commands that we're familiar with already. So let's say, for example, rotate. If we plug this in to here, then it's rotated this around by 90 degrees. Or if we type in scale, then you can see that this has scaled it by a factor of 0.5. Or any of those other commands that you've known, that you know how to use inside of Rhino, they will exist inside of Grasshopper as well. You'll see here, as if we go into our Rhino window, that if I go to move this particular geometry like so, that it's actually going to re-reference it inside of Grasshopper itself. So it's going to stay connected in here, which means that I could design something inside of Grasshopper, and then I could change the inputs inside of Rhino, and all of those commands are going to continue to operate on whatever geometry it is, even after I've edited it. So it's a very flexible way of designing. Now, the other way that we can make a surface is by typing in surface, and you'll see that there are all of these different options for creating surfaces. So we could say plane surface or 4-point surface, or if we go to these surface tools over here, we can see that we could loft it, or edge surface, or boundary surfaces, or extrude this, or patch, or pipe. All of these are hopefully commands that you'd be familiar with already. You'll see as well that when we create surfaces here, so if I was to do this point-to-point surface, it will ask what I want the first corner of the plane to be. And then once I reference this, it'll ask what you want the other corner to be. Rhino itself works in a way where it actually scripts things out, but you're doing it visually. Grasshopper just does it in terms of the code itself. So what I mean by this is that if we double click on the Grasshopper canvas and type in plane surface, and we'll select this component here, then what will be given is a component that looks like this. So it's different to what you've seen already because it's got multiple node inputs. If you're wondering what these mean, then there's a great way of actually doing this. You can right click on this component and you can say help down the bottom here, and it'll actually give you an explanation of what each of these inputs are. So for X size, it says the dimension in the X direction. So it's going to be the size of the surface in the X direction, and then the dimension in the Y direction. So the size in the Y direction along here. And then it asks for a plane as well. So that's basically the point that it starts at. So what I could do is that I could make a surface, and maybe I want it to be 20 meters along. And to do this, what I need to do is I need to create a number input. There are a few ways of doing this. The easiest way is to use what's referred to as a number slider. So if you put in any number, let's say, for example, 5, it will prompt you to create a number slider. And by default, this number slider will slide anywhere between 0 and 10. So it's the same order of magnitude as the number that I put in. Whereas if I was to say that I wanted it to be 50 and hit enter, then now it's going to create it between 0 and 100. Or if I was to say 0.1, it's going to create it between 0.1 and 0. If it was 0.2, it's going to create it between 0.0 and 1. And so what I might do is that if I wanted it to be 20 meters, I can put in, and currently my model is in millimeters. Sorry for anyone in the US or Liberia that's using the imperial system, but I'm going to put in 20,000, which is 20,000 millimeters or 20 meters. And this is going to be the size of my plane that I'm creating. And what I can do is that I can drag out from the end of this number slider and drag it directly into these inputs here. So just to reiterate, what I'm going to do is I'm going to put the cursor over the end of this number slider. This is referred to as the node. And I'm going to click down with my left mouse button. Then I'm going to start dragging this wire out. And I'm going to drag it towards the input of this plane surface node. And then once it's over that node, I'm going to release it. And then this is going to create a wire connection between these two components and drag it into this input here. And this is a way of like visually coding rather than, for example, writing out Python or C# script. We're going to be doing this visually. And then we can zoom out and you'll see that it's created a surface that is 20 meters across. Now, the great thing about this is that we can change this parametrically. So if I wanted to, I could, just change it around like that or undo that number slider change. Now, the next thing that I want to do for this exercise is that I'm going to break this up into a grid. And maybe to do this, I'll go into my top surface and I want to show you another trick. See how this currently isn't zoomed into this geometry? What we can actually do here is we can select whatever geometry we want and then right click on the canvas itself. And one of the options here is to zoom. And so if you click on zoom, it'll actually zoom in to fit the exact size of whatever you happen to have selected. It can be a really, really useful shortcut. The next thing that I'm going to put in is something called a grid structure, which is this component here. And what this allows us to do is that we can take a surface that we've created and then we can make a certain number of divisions. What I might set here, I might set 10 to start off with, just so it's not too close or too far, or not too many and not too few. And then I could change this parametrically as well. Now, you'll notice that when I select these, it actually changes the color that it displays as inside of the Rhino window itself, which is a really useful way of you diagnosing or seeing what you actually have selected and what each part of your script is and does. There are a few different options for changing this around. The first thing that you could do is that you can select something and then you can right click on the canvas and you could say preview off. When you right click on the canvas, it lets you turn the preview on or off for multiple things at once. Whereas if you select a component and you right click on the component, you can turn the preview off for this component individually. So even if you've got multiple things selected, it'll only do it individually, whereas if you do it on the canvas itself, it'll turn the preview on or off for multiple things at once. The second thing to note is that you've got all of these preview settings up the top right-hand side here. There are a few really important ones, and you can see that they're sort of divided with this line here. So this red one here, and the three that are next to it, change the way that this is actually displayed. So if we select this red one, it will display normally. If we select this Y one, you'll see that it'll display in wireframe. So this is sort of the difference between wireframe view and shaded view. And then if we select this one with a darker base shadow to it, it'll hide everything. So it won't preview anything whatsoever. The other setting that I want to show you, which I think is actually really, really useful, is that if you click this green box here, only the things that you have selected will actually be visible. So if I select grid structure, only the grid structure will be visible. If I select plane surface, only the plane surface will be visible. And so if you don't have anything selected, everything will be hidden. We'll come back to this later because it'll be a really, really useful tool for diagnosing issues. All you need to do is click on it and it will actually get rid of, or it'll start showing everything up again. You've got two more settings which aren't really very important. The first one is your preview settings, which is this button here. It's the yellow and white circle. And with this, you can change the color that either the normal or selected geometry is displayed in. So you could change it, instead of being red, maybe you might want it to be in pink or something like that, up to you. And then the last one is the preview mesh quality. So this will change the quality at which all of your meshes are displayed, or all of your geometry is displayed, which can be really useful if you're, for example, altering hundreds of thousands of pieces of geometry at once.
The next thing that I'm going to do is show you a range of techniques to keep your scripts clean and organized. It's shocking how often I come across people's scripts and they look something like this. This is an issue because it's extremely hard to read or discern what this script does, and it's going to be even more difficult to make changes or fix the script itself. Ideally, what you should be doing is using a range of techniques, so things like grouping, labeling, color coding, adding nodes, or adding explanatory notes to your script so that they're as beautifully structured and easy to interpret as this script is. The reason that we do this is because even if you understand the script right now, when you come back to it in a couple of weeks' time or a month's time or a year's time, which we do tend to do, you're going to have a very hard time interpreting what each part of it actually does and how you can take particular parts and maybe apply it to future projects or even just edit it as it sort of currently stands. This is even more important if you're working in a group environment because it is extremely difficult to read scripts and to make changes to scripts and understand the consequences of making changes to scripts if they're not beautifully and cleanly well organized. Especially if you're working in practice, it's an absolute disaster if somebody's written a Grasshopper script and the building is designed in a particular way and then that person ends up either going on long service leave or they might end up retiring or something like that, or moving to a different practice, and then the entire practice is crippled because nobody really understands properly how to actually make changes to this script.
The first way to start organizing your script is to group elements together. And to do this, what you can do is you can select geometries and you can right click and say group like this. By default, your color will actually be purple. And there is also a shortcut to do this, which is that you can select two pieces of geometry and you can hit Control G and it'll create this grouping. By default, my color is white. You can change the color that this is previewed in by right-clicking on the group and saying color, and then you could set it to any color value that you want. So just change the hue and the saturation levels or the value or the opacity down here. By default, it's purple, which is really good, or you could choose any other color. I've made mine white, and the other thing that I've done is that I've set make color default, so that whenever I make a group in the future, it'll always be displayed as white. Now, the next thing that we can start doing here is that we can start labeling these groups themselves. If you right-click on this group, you can make a label that says, for example, surface for panels, because this is where we create that surface. And this will be a little explanation of what this actually does. I very, very strongly encourage you in the highest possible terms to make sure that you group things and to label them as we go along so that all of these parts of the script make sense to you. The final thing is that we can go down here, and if we double click and we say scribble, we can choose this component here, and this will let us place text. All you need to do is double click, and we can say introduction to Grasshopper by Legacy Design Studio. And then you could change the size or the font as well, and you can create a top label to this, or headings like this. And if you wanted to, you could group these elements as well and change the color of them to whatever you might sort of want it to be. I'm going to delete it for the time being because even though it's great advertising, I think it's a little bit distracting. Now, the next step that I'm going to show you is that you can start organizing your wires in different ways and also all of your components in different ways. So if I was to have another number slider here, like this, and another number slider here like this, and they were not very well aligned, it is going to really play with my OCD because I love having everything extremely organized. So if we select all of these at once, you'll see that there are these little icons down the bottom, tiny little icons, and they actually allow us to align elements. So if we click further to the right hand side like this, it'll move them all as far right as the furthest right component is. And if we were to drag this down like this and then select them again, and we click the bottom one, then it's actually going to align them vertically like this so that they're perfectly aligned together, and it's going to create even component spacing. The other thing that we could do here is that, which is really important, is that it's very, very important for your scripts to read from left to right, and also for wires to not be running all over the place. So there are a few settings for this, which I'll reiterate later on, but I want to introduce you to them now. The first one is that you can double click on a wire, and you'll see that it puts in this thing called a relay. Relays can be really useful because it can help you to actually it can help you to change how the wires go across your scene. It doesn't really matter too much here because we've only got a few pieces of geometry, but as we start to build up our script, this can be really useful. The other thing is that you could right click on this relay and you can label the information going through it. So we could say surface for grid, and you'll see that anything downstream from this will actually be labeled as well. If you delete these relays, it'll just delete them but keep the connections between these different nodes. You can also change the style that these nodes are displayed in. So if we right click on this input here, we can say Y display, and then we could set it to either be faint or hidden. So faint will make it a lot more faint like this, or hidden obviously will make it be hidden, and it'll show that there is actually an input with this icon, but it will not display unless you select the component itself. So if I right click here, we can go Y display and set it back to default. So I'm going to start showing you how to create that point attractor system that we were going through earlier. And to do this, the first thing that I'm going to do is start by making a bunch of circles. You'll see here that there are two components for circles. So this is where we reference in geometry from Rhino itself. Hopefully you recognize it being black. So we don't want to use this. If we click on this, you'll see that there's no, you'll see that it's actually turned orange and that there's no inputs. And this is because we can right click here and say set one circle from Rhino itself. So we don't want this one. That's what's referred to as a container. We want the component itself. So if we type in circle, we want this command which creates a circle. You'll see that there will be multiple inputs for this. So the plane being the position that we have the circle in, and then the radius being the size of the circle. So what we can do is we can take this circle over to here. And what we're going to use is these. You'll see that there are two outputs here. So there's the lines, which are all of these curves, and then there are these structure nodes, which are actually all of the points that all of all of the edges of the surface grids are made up of. So we can take these nodes and plug them into our plane here. A plane is basically the same as a point. A plane is actually just a point with an orientation, but we can use these terms interchangeably until I explain it in more detail a little bit later on. At the moment, you can't see it because our circles are so tiny. So what I'm going to do is create a number slider, and maybe we'll set it to 1 meter each, so 1000. And now you'll see that it will make circles across this entire surface itself like this, which we can change parametrically. You'll notice sometimes that when we input components, so if I put in our next component, which is going to be called curve closest point, and it looks like this one here, that it will be orange instead of being this white color. It means that no inputs have been labeled here yet. So it means that there's nothing referenced for this point, and there's nothing referenced for this curve. A way to actually see what is running through this is that you can hover over the either inputs or outputs. So if we hover over here, you can see that it says structure nodes, and then it lists all of the geometry here. So there's 121 locally defined values, which are 121 points, and then it'll list all of those points there. But when we hover over here, it'll say empty point parameter. It means that no points have been set as of yet. Same for curve here. So it will say empty curve parameter. Whereas when we start referencing these things in, you'll see that the color will change. So let's start by typing curve or CRV, and we can reference another curve container here. And what I'm going to do is that I'm going to create a control point curve inside of Rhino itself, like this, and then enter. And what I can do is then say set one curve, and select that curve, and hit enter, and then it will be referenced inside of Grasshopper itself, and I can plug this in here. And then I can take all of our points that we created in this grid structure, and I'm actually going to plug this into our points here. You'll see that as soon as I do that, it will turn white like this. So white means that it's all running perfectly. Orange means that nothing's been referenced. I'll note one more thing, which is if we were to plug in these curves, so these are the curves instead of the individual points, and we were to plug the curves into this point input, it's going to turn this entire component red. And this, when it turns red, it means that the component isn't able to function. You'll get a little explanation of why this is on the top right hand side if you hover over it. So it says here, data conversion failed from line to point. So it sometimes gives you a little bit of a hint about why it might not be working. So when it says that lines were inputted instead of points, it can make you think, oh, actually I put in these lines, whereas what I meant to do was put in the nodes, which were all the points themselves. Now, it looks like we've got heaps of stuff going on here. So what I might do is I can start by actually turning the preview of some of these geometries off. The first thing I might do is I'll turn the preview of this grid structure off. And I might also turn the closest point off in a second after I show you how this works. What curve closest point does is that it takes our curve and it takes all of the center points of these circles or the nodes here, and it will actually find the closest point from each of these to our curve here. So to display this, we could create a line. And again, we're not using the container, we're going to use the component itself. And we could create a line between the closest points on the curve and the structural nodes like this. And you can see that it's finding the closest point from each of these nodes to the curve itself. The other thing that it can display is it displays the data, which is the distance from each of these points to the curve itself. And these are going to be displayed numerically. I'm going to turn the preview of this off so that it looks a little bit cleaner, like this. And we're just going to have another little bit more of an in-depth look at this component. So all of these distances, I can hover over and it'll say that there's 121 distances. If I hover over the points, it'll show that there's 121 points. Another way of displaying this geometry is we can use something called a panel. Panels have a few different uses. Firstly, if I wanted to, I can plug anything into a panel and it'll show what data is actually displayed in this. So in this case, it displays all of the distances as numbers. The other thing that panels can be really useful for is that if, for example, I wanted to create an explanation somewhere here, I could type in panel and then start to double click. And I might say, this part of the script creates the plane surface like this. And then I could make it a bit smaller, or I could add it to this group like that. And the final thing I could do here is that I could right click and change the color itself of what the panel is. So if I wanted to, I could make this panel gray, and I could think to myself that any explanations of how this script works can be gray in the future. I really encourage you to use this as you go through to take notes of what each part of our script does. So the next thing that I want to do is that I want to be able to use the data of this distances to change the radius of our circles. So what I mean by this is that any circles that are really close, I want these to be quite large, and any circles that are really far away, I want them to be much, much smaller to create that parametric relationship between these elements. And so the way that I might do this is that I can use a little bit of mathematics. I might multiply the values of these distances by the radius of this circle. You can see at the moment though that if I was to multiply 500 by 900, it would create an enormous result. So I can start using some of the maths components.
Just a quick disclaimer, you absolutely do not need to have a good understanding of maths to be good at Grasshopper. I would say that 99% of modeling in Grasshopper requires zero understanding of mathematics whatsoever. Having said that, I do want to teach you a few things so that you've got a really holistic understanding of what this program does. And for those of you that do enjoy maths, then there are some really gnarly applications like these minimal surface geometries, which you can define with particular equations like this to actually create these geometries if you wanted to explore mathematical concepts. But yeah, for 99% of Grasshopper applications, you do not need to use mathematics whatsoever.
What I'm going to introduce you to is a component called reparameterize. This one here called reparameterize numbers. And what this lets us do is that we can connect our panel over here into the reparameterize numbers. And if we were to create another panel over here, it can show you what the numbers will be once they actually come out of this. And what it's doing here is that it's taking each of these, or this whole set of numbers, and it's remapping those numbers so that the largest number, whatever that may happen to be, it might be 20,000, is going to be remapped to be 1, and the smallest number, it might be like 400, is going to be remapped to be 0, and every other number in that set is going to be made to fit within 0 and 1. And then we can use the multiplication function here. And what I'm going to do is that I'm going to multiply this number here by our original radius. And then I'm going to plug it into this radius component here. And now what you'll see is that I've got a parametric relationship between this curve and the size of these circles. So if I was to rotate this curve, it's going to change the way that all of this is displayed. And this is the really powerful thing about Grasshopper, is that Grasshopper allows you to manipulate lots and lots of data at exactly the same time in lots of different ways, in like a varied way. So instead of modeling each of these individually, which would take ages, it's going to allow you to manipulate heaps and heaps of data all at once. The next thing that I might do is I might start labeling this out. So I've shown you how to do scribbles and panels and groups. What I sometimes like to do is create groups around individual components that are a much more saturated color like this. So I could say here, this is the curve for attractor logic, like this. And then I might reference this as to be red, and I could say that this is the radius of the circles, or the largest circle. You can see how this will make the largest circle bigger or smaller. Okay, so the next thing that I want to do is I want to show you how we can take this geometry from inside of Grasshopper itself and then put it into Rhino so that we can edit it in exactly the same way as we're editing this curve. And to do this, we're going to use a process called baking. And before I do this, I'm just going to minimize Grasshopper here, and we're going to make a couple of different layers. So one of them will be called, let's call this Grasshopper Bake. And we can change the color of that layer as well. So let's make it maybe a green color. And I'm going to show you two ways to bake this geometry. First of all, what we can do here is that we can pick a particular component. So we might want to pick these circles. And the two ways that we can bake this are either by clicking on the component itself, or by baking when we click on the Grasshopper canvas. They're going to bake in two very different ways. When we bake clicking on the component itself, it'll give you this menu, and you can choose what layer you actually want to bake it onto. And you can choose color by layer and a few other different options, like grouping, which can be useful. And when we press OK, you'll see that it will bake out to this layer. But using this approach, you can only bake one component at once, and it's a little bit of a time-consuming process. So I'm going to show you something else, which is that we'll call this layer Bake Canvas. And see how at the moment the active layer is the default layer? What I'm going to do is I'm going to activate this Bake Canvas layer, and maybe we can make this a shade of pink. And what we can do here, if we go back to Grasshopper, is that we can select something like maybe the plane itself, and maybe we could select the points as well by holding Shift and selecting that component. And what we can do is, instead of clicking on the component itself, I'm going to click on this, the canvas, so an empty space, and I'm going to click Bake. And what you'll see is that it's baked everything out that we had selected, and it's baked it immediately without any options, and it's baked it directly onto our active layer. Now, the next thing I want to show you is that you can minimize your Grasshopper window like I showed you earlier, but you can also exit out of it. If you exit out of it, it won't actually close the Grasshopper file. It'll just get rid of the preview. So it'll only get rid of the preview itself, and when we go back into Grasshopper, everything will still be open. So this can be useful to sort of hide everything in that Grasshopper viewport. And you'll see now that we've completed this process of baking that this geometry exists inside of Rhino itself, and you can edit it inside of Rhino. And if we go back to Grasshopper, you'll see that it's not changing the references of what we've actually created inside of Grasshopper itself. So the next general question that you might be asking is, how do we save these files? And to save these files, we need to save both a Rhino file as well as saving a Grasshopper file separately. So they're two distinct files. We can type in save, like you would normally do inside of Rhino. And I might call this tutorial part 1, general overview. And then I might save this file here, so saving it separately as tutorial general overview as well. So the exact same file name. And you'll see that we'll have our Rhino file here and our Grasshopper file here. You'll see that our Rhino file at the moment is quite small. So this is only 175 kilobytes or 0.17 megabytes. And this is even smaller. This is 10 times smaller. If we change out this geometry from being a circle into a sphere, what we can do is that we can move these Ys by holding Control and Shift at exactly the same time, and you can actually transpose Ys from one component to another. So we're going to hold Control Shift and drag from here to here, and you can drag multiple geometries at once. And I might bake these out, and then I'm going to save this file, and I'm also going to save this file. Now, what you'll notice is that once I've saved this file, it's going to be substantially larger. So now this is a 24 megabyte file. But when I save this file, which is effectively exactly the same thing, that this file is still only 18 kilobytes large. So Grasshopper files are actually very, very small, very, very compressed file sizes. And the reason for this is because every time that you start open this Grasshopper file, it doesn't actually save the geometry itself. It saves like the recipe to create all of this geometry. So it takes a lot longer to compute when you open this file compared to when you open the Rhino file itself, but it's a much smaller file size. And the wonderful thing about this is that once you actually save a file inside of Grasshopper, it will continuously autosave every time you make an adjustment. So every time you plug in a new wire, every time you make a new component, as long as this file is saved, it will constantly be making an autosave file. And the way that we access this is that you can go File, Special Folders, and then Autosave Folder. When you go to this folder, you'll see that there is a list of all of these different files, and they're constantly saving themselves. So whenever Grasshopper crashes or Rhino crashes, you've always, generally speaking, will have a backup of that file that is completely up to date. Unlike Rhino, which autosaves every sort of 10 to 20 minutes, you'll always have a backup of your Grasshopper file, which is really, really helpful because it can crash quite a bit if when you're learning to use it for the first time, but we'll work through that and try to minimize that as much as possible for you. The last thing I want to show you about managing files and saving them and opening them is that you can actually be running multiple files at once. So if we go File up the top here and then say New Document, it's actually going to create like a completely blank canvas that we can start making a new file in. And the way that you change between multiple files that would be running at once is that you can click up on the right hand side here up the top, and you'll see that we've got this tutorial part 1, which we were just using, and then we've got this new unnamed, and then there's also a third file here, which is actually what we're going to go through in the second part of this tutorial, which is going to give you much more in-depth understanding of Grasshopper components and skill sets. And it's great because I can be running all of these files all at once, sort of quite exclusively, and switching between them very, very easily. Now, the final thing that I'm going to show you in this example is how we can retrieve items on lists. So instead of baking all of these out at once, how you might retrieve only a few individual circles from this actual list rather than all of them together, because this is what makes Grasshopper so powerful, is the manipulation of data. It's very easy to use commands in Grasshopper the same as what you would in Rhino, and what I mean by that is it's very easy to take a curve and then extrude it, but it's not more efficient. What makes Grasshopper efficient is being able to manipulate heaps and heaps of data all at once. And so this is going to be the first step in actually understanding how to do that. So to do this, what we're going to do is we might go to our spheres list here, and also I'm going to press Ctrl-Z to unbake all of this geometry that I've just baked out, so that we're back to just having things inside of Grasshopper and not inside of Rhino. And what I'm going to do is I want to actually select the largest circles and sort them from the smaller circles. And so what I'm going to do is I'll delete this, and we'll just take our spheres here. And to do this, what I'm going to start with is a component called list item. It's this one down here. So it says list item. The other thing that you can do inside of Grasshopper when you want to find particular components and where they are and components that might be related to them is you can hit the Control and Alt keys at the same time, and you'll see that this icon comes up, or maybe it's Command Alt in Mac. And then you can click on your component here and it'll actually show you where it is inside of the top menu. So see how this little arrow is actually showing where this is? And if we click down here, you can see all of the different items that are associated with finding or sorting or partitioning various lists and manipulating data in that way. List item is the one that you'll probably use the most. And the way that this works is that if we plug it in here, you'll see that there are 120 items on this list, so it means 120 circles. And if we make a number slider that's maybe, we'll put in the number 87, so we'll get a number slider between 0 and 100. We can plug it into this index here. And what this is going to allow us to do is select a particular item on this list. So this is selecting item 86 or 85, or we could work our way to be a little bit higher. So this is item 97 on this list. We can also select multiple items together, so we could have item 97 as well as item 98. And to plug both of these in, what we can do is start dragging this wire and then hold the shift key down, and you'll see that there's this little icon to plug in multiple inputs at once. If you want to disconnect this, what you can do is you can start dragging the wire out and then hold the Alt key, and you'll see that it goes red like this, and then you can plug that in and it'll unplug it. The other option that you have for this, if I press Ctrl Z, is that you can right click on this input and say disconnect, and you can choose a particular number slider that you want to disconnect as well. If you hold Alt and start dragging without already selecting the node, what this will do is it'll actually create space. So it's a way of organizing your Grasshopper scripts and creating space. So again, you just hold Alt and then you can drag out like this and it'll create space if you want it. Now, maybe I don't want an individual number like this. Maybe I want all of the numbers up until 86. And so what I could do here is that I could use a component called series. And what series does is that it creates a set of numbers up to what you have actually specified here. So if I plug 86 into that count, like this, and then I use a panel to see what data is actually running through it, you will be able to see that we've created a numbers slider that goes all the way up to 86. So there's 86 numbers here, starting with the number 0. And so if we plug this in instead, you'll see that instead of having just one number that's included, it's going to have all 86, or we can go all the way up to 100. If we wanted to delete items on the list instead, we can use the Cull index. And this is the opposite of list item. So when we plug this list in here, and then we plug in series into the indices, it's going to cull all the way up to the 100 numbers. So it's doing the opposite of what list item does. The thing that you should be noting about this is that all of the list is in a particular order like this. So this is the natural order, but we can also sort these items in the list using what's referred to as a sort list component. And what sort list requires is values that you want to sort. So in this case, this is the list that we want to sort, which we can plug in here. And then it's also asking for keys. So keys are a set of data that we're going to use to sort with this. To give you an explanation of how sort list works, if I use another sort list component here, and then I use a panel, and I might put in some numbers, so 3, 7, 4, 9, 2, 6, like this. I can plug these into keys, like so. You'll see that by default it'll turn up red, and that's because this is currently reading as text rather than as numbers. I'll explain in detail what this means later, but for now just right click on it and say multi-line data, and this will turn it into data rather than text. Again, I'll explain this a little bit later. And then we can make another panel over here and plug this in. And what you'll see is that it's ordering this list from smallest number into the largest number, like so. And what the keys will do is that it'll order that data in parallel to the way that we order these keys. This might feel a little bit overwhelming at first, but it'll start to make sense very, very quickly once we've gone through 2 or 3 examples of it. And so what you might want is a way to actually sort all of these lists out. And the easiest way that we can do this is with all of these distances. So we've got 121 distances, and what this represents is the distance of each of these spheres to its closest point on the curve. And so if we plug this into our keys over here, and then replace this into our list for list item, and I can delete Cull index, then what you'll see is that all of the first items on this list will be the smallest spheres, and then the ones that are left over will be the largest spheres. If I hide all of this, it'll become easier to see. So it'll go from the smallest to the largest, because that's the way that we're sorting this list, because it's the size of the sphere is dependent on its distance to the curve, and then its order in that list is also dependent on the distance to that curve. So it's only giving us the smallest of those spheres. Again, we're going to go through heaps and heaps of different examples of this. So even if it's feeling a little bit overwhelming at the moment, just stick with it, keep working through, and it'll all start to make sense by the end of this tutorial. Okay, so to get started with this part of the tutorial, what we're going to do is we're going to go to File up the top here, and we're going to make a new document because we're going to be working with a clean slate. I also want you to make a new Rhino file. And we're going to choose Objects Millimeters. And let's minimize this Grasshopper window, and we can maximize the perspective viewport. And then go back to Grasshopper over here. And now we can get started.
I also wanted to preface that we're not going to be working at the scale of a full building. So for this exercise, I thought that it would be better if we didn't have very, very large numbers. Like if you wanted a building that was 10 meters across, it would be 10,000. So instead, what we're going to be working at is the scale of an architectural model like this. I used to build these and sell them. I'm sorry, but they're all sold out. I used to really love them because they're reminiscent of these like models that carpenters used to make at trade schools to practice their craft, and I thought that this sort of feels like a little bit of an extension of that. So the scale that we're going to be working at is this, just so that you sort of have a degree of understanding about why we are inputting the numbers that we actually are. The other thing is that Grasshopper doesn't care what units have been set. It will just reference the numbers in your Grasshopper script and then apply them to whatever units you've got set up in your Rhino file.
Now, I might also mention that you can download all of the scripts that we go through in this tutorial so that you don't actually have to write it up yourself, or if you miss a step or whatever else, you can just open the scripts up. And to do this, we just go to the courses link in the description, and you can explore the full courses library. There are two ways to access it. So you can get lifetime access where you just click buy once, or you can get monthly access. You'll notice that when you hit buy once, that it's a really easy process. You just put in username, email, and what you want your password to be. And then we can go back to design courses once you've signed up, and you can click this link here which says explore the full courses library, and you'll have full access to all of the different resources. So all of the fabrication resources, all of the different modeling resources, but also under the Grasshopper introduction and overview, if we click on this, you'll see that we've got a free download for all of the tutorial scripts. So if we click download, you'll see that it downloads this file, and we just need to right click and say extract all, and then say extract. And you'll see that it creates a normal file here, and this has got all of our scripts in it. So you'll see that when we drag this in, it will automatically have all of the things that we're going to go through in the next script. And we've got all of the scripts in this folder here that we're going to run through in this tutorial. So the first thing that we're going to do is that we're going to set the base point for this pavilion. I have a few options to do this. I could, for example, place it a point in the center here, and we could type in point, and then say set one point by right-clicking on that point component. And you'll see that this will be parametrically linked. But what I want to do instead is I'll delete that point, and I'll delete this point component, and I'm going to construct this point parametrically inside of Grasshopper itself. And I can do this with the construct point component, which is this one here. And what this lets me do is that I can specify the position of a particular point in terms of its X, Y, and Z coordinates. So see inside of Rhino how the green axis here represents the Y position. So if I was to say, for example, 100 in the Y position like this, it would move it across like this. Then when I plug it into the X position, see how it changes it across the red one? You can see this down here according to this axis, and the Z coordinate is the height. So this now adjusts the height as well. But what I want is for this point to be dead in the center of our Rhino model. So I'm going to set the points as 0, 0, 0. And very basically, this is our complete first step. This is where we're going to start making things. In this tutorial, what I'm also going to do is help you to group and color code and label this entire script so that you can actually really easily read this later on and understand how it works, and hopefully this provides a degree of clarity for you as you go forward. So I'm going to select these components, and then I'm going to right click here and say group. The shortcut for this again is just hitting Control G, and by default I've got white. You might have purple or any other color that you've set, and I'm actually going to change the color of this to be maybe a pastel blue shade. So I can just change the saturation and then change the hue around like this. And then the next thing I might do is I'll say scribble and get this scribble component. And then I'm going to label this as part 1, so 1 dot, and then set base point. And I might make it a little bit larger as well over here. And what I can do with this as well is that I might put this into a group by hitting Control G, and I might change the color of this as well. So this could be maybe a much more saturated version of that color. And actually I might change the color of this group as well to be a little bit greener or a little bit more like aqua colored, a little bit darker, like that. Okay, now we can start with part 2, and part 2 is going to be creating the base pavilion, or the base of the pavilion. So I'm going to take this and I'm going to press edit and then copy, and then I've got 2 options. So one is that I could say paste in place, or I could paste it in the center of my current Grasshopper canvas, because hitting Control V is always going to paste it back where it sort of started. And I'm going to grab this and I'm going to change the text by double clicking on it, and I'm going to say 2.create pavilion base. And then I can right click on the group and change the color of that group, and maybe we'll go for a more saturated or a darker blue, like this. And we can probably move this to over here. And I'll drag this out just so it's a little bit easier for you to follow along with a much larger canvas. Okay, so the first thing that we're going to do with this is we're going to create a circle for the base itself. So I'm going to type in circle here and hit enter. And I'm going to use our original point and plug it into the plane for where this circle should be. So if I was to change location of the point, it's going to change where the circle is. And then the next thing that I'm going to do is I'm going to set a radius. So I might set a radius of 100 millimeters. Like so. And you can see that I can just adjust this parametrically as well. Now, at the moment, this is currently a curve. If we were working inside of Rhino, we would use that command planar surface, but I want to reiterate that planar surface inside of Grasshopper, for a reason I'm not quite sure of, but I'm sure that there's a very good reason for it, is called boundary surface. So let's type in boundary surface. Just one of the few commands that isn't actually the same name as what it is in Rhino. And we can draw this out, and this is going to create a surface. And the next thing that we're going to do is that we're going to turn this surface into a poly surface. And we're going to do this by extruding it. So if I double click here, I can type in extrude. And there's no extrude curve or extrude surface like there is inside of Rhino. There's only an extrude. And this can work for both. So we're going to set the base here as this surface. And the other thing that we need is a direction. So what we're going to use for this is a vector. Vectors are basically a direction with a given distance. For the purpose of this, what we might use is actually the inbuilt Z vector. So it means like the up down. See how it's labeled Z down here? So you can type in unit Z like this. But if we wanted to, we could also use any of the other tools for creating vectors, which you'll find here under vector. So things like vector XYZ, which can let you create vectors by setting units in the X, Y, and Z direction, or a vector 2 point. So as the name suggests, creating a vector which is a value between 2 points. And there's a few others here that we're going to go through later on in this tutorial as well. So what we can do is we can plug this in here, and by default, if we hover over this, you'll see that there's a factor of 1. Heaps and heaps of these Grasshopper components will have values already set into them, even when you don't connect a number slider. You're actually able to change these by right-clicking on this input, and you can set a particular number. So if we wanted to, we could set 20 and say OK, and this is going to extrude it up by 20 units upwards. But I think that it's a lot better if you visually show this using a number slider. So what I might do is I'll create a number slider with a value of 5 and then plug it straight into this unit vector like this. Now I'm going to start labeling all of this out as well for you. And what we might do first is we can create a group here, and we might call this as base circumference. And then we could group all of this together as well. And we can right click here and say thicken base. I always like to try to keep all of these lines straight so it's much easier to read. So I might move this down here as well. And then maybe this can be moved over here. Okay, so the next thing that I'm going to do is that I am going to actually create a pipe that runs around the edge of our pavilion base, and the reason that I'm going to do this is to smooth off the edge so that it's not as harsh. And the way that I'm going to do this is that I'm going to take our original surface curve that runs along the bottom here, and I'm actually going to pipe this curve. So I'm going to use the pipe component, and I'm going to plug in this curve. And I want to create a parametric relationship between the thickness of the pipe and the thickness of the base so that it's always the same thickness. And so here we've made this a value of 5, so like 5 high. If I plug in the 5 here, you'll see that the radius is twice the radius of our base itself. So to make this relationship parametric, we need a value that is half of 5. And for this, we can use the division tool. So if you type in division, then we can divide this number by 2. And now, no matter what height we actually set this base at, it is always going to have the same circumference as this pipe. However, you'll see that it's not in the right direction. So what we actually need to do is move it upwards a little bit. We need to move it up half the amount that we move this unit vector upwards by. So vectors can also be divided as well. So if we type in division one more time, and hit enter, then we can actually take this unit vector and we can divide it by 2 as well. Like this. See here how we've got this Y that actually runs through all of this? What I'm going to do is I'm going to create another node here. So you can double click here and it puts in a relay. And this is going to clean everything up a little bit. And now what we can do is we can use what's referred to as a move component. So when we move things, we need to set the geometry that we want to move. And then we also need to give it that vector or that motion. Now, you can see that this original pipe is currently visible, but so is our moved pipe. So what I'm going to do is that I'm going to turn off all of this original stuff, so like the circle and the boundary surface, and I'm only going to have the extrusion and the geometry visible. I'm going to do this again just to reiterate that by selecting everything, and then I can right click on the canvas itself and then say preview off. And now you'll see that I've got this extrusion and I've got this pipe. And what I can now do is that I can change the circumference of the circle parametrically like this, and the pipe will always change. And I can also change the thickness of this, and this will also change the size of the pipe as well. Now, there are a few ways to combine these two elements onto one list. So if we hover over this, you can see that the data that's running through it is one closed brep, and you've also got one untrimmed surface here. Basically, it's just two poly surfaces or two surfaces that are on separate lists. And the way that we can combine this is that we can use any of these geometry primitives that we've gone through before. We could use breps or surfaces because I think both of those would work, but what I prefer to work with is something referred to as a geometry box, which is this one down here. Or you can just double click on the canvas and type in geometry and hit enter. And what we can do with this is that we can put any geometry inside it. And so we'll start off with this original extrusion. And then what we can do is we can start dragging out this move geometry and then hold down the shift key like this. And then because we're holding down the shift key, we can actually put both of these onto the same list. So see here, if we use a panel tool to visualize what's inside this list, you can see that there are two items here. So we've got this closed rep and this untrimmed surface. And when we select it, we can see it all goes that one color. So we can select all of this and turn your preview of that off. And I'm going to delete the panel as well. But what I want is that instead of these being two separate elements, I want to join them together. If we were to do this inside of Rhino itself, what we could do is we could go to our solid tools and we could use Boolean union. But inside of Grasshopper, it's called something else. It's actually called solid union. If there's ever a component that you can't find, what I suggest doing is just going through here and having a look at what each of these general tabs say up the top. So this one, for example, is labeled intersect. And here we can see like shape intersects. And you can have a look at what the different, I suppose, options are for shape intersect. So you could have like mesh union, mesh split, mesh difference. In the same way, we've got solid intersection, solid difference, and solid union, or split brep, which I'll go over a little bit later, or regions. We're going to be covering almost all of these, but in our case here, we're using this one called solid union, which is the equivalent of Boolean union. And what I'm going to do is just plug this in here, and this is going to bring us onto the first most basic part of data manipulation. If we use that panel one more time, what you can see here is that we've got these two items, but they're divided by these particular numbers here. What these are referred to as are branches on a tree. And so what this means is that these two pieces of data aren't aligned with each other. So if, for example, we start dragging this panel and hold Alt, we can duplicate that panel outwards, or you could just double click and make another panel. And if we visualize what's coming out of here, you can see that this solid union hasn't actually worked. So when you feed this data in, if you want this component to combine these two parts, they need to be what's referred to as on the same branch. I'm just going to start you off very, very basically here. To do this, to put all of this data onto one branch, the most basic way of doing this is flattening data. And to achieve this, what we can do is right click on this component here, and you'll see that you've got these different options for lists here. We're going to go over each of these in the next little while, but for the time being, we're just going to cover flatten. So if we flatten this, it puts all of this data onto one single branch like this. And because all of that data is on one branch, it's going to actually combine this in the solid union operation. Again, I don't expect you to sort of understand this completely. Just bear with me for the rest of this tutorial, and I promise you that you will be feeling much, much more confident with it by the end. Now, the next thing that you may notice is that underneath this solid union component, it says 356 milliseconds. You probably don't have this yet because it won't be enabled, but what I've actually got here is something that tells me how long each component is actually taking to compute. And the reason I'm doing this is because some Grasshopper scripts can actually run for a very, very long time. And so what we want is we want to understand which components are taking a long time so that we can limit the amount of time that they take to actually compute. To understand how much time something's taking to compute, we can go to display and then canvas widgets. And the canvas widgets that I want to use here is referred to as the profiler. Once you activate this, it will start to tell you how long each component actually takes to compute. It's not telling me for these ones here because it's not actually meeting a particular threshold, so it's computing so quickly that it's not letting me know. But for more complex operations like this solid union, it is letting me know. If I double click on this, it can tell me what percentage of the script this computation takes up. So this is actually taking up 99% of the time overall that it takes to compute all of this out. So I'll double click that again and it'll give me the numerical number. And following this, I'm just going to delete those panels, and I'm also going to start to label this again. So I'm going to hit Control G here and move this down, and I'm going to label this as smooth edge for base, because that's effectively what this is. And then I'm going to select all of this geometry, or all of these components here, and then make a new group. I'm going to make it the same color as our title over here so that it's color coordinated. I might make this a little bit more saturated as well, just so it looks pretty. And then I can set a much more desaturated version of that color as well for down here. You'll see as well that on this side, I'm not actually swiveling around the base itself. So what I can do is that I can select this component here, and then I can right click on the canvas. It's not going to work if I right click on this group. I have to right click on some empty canvas, and I can say zoom, like so. And now you'll see that I actually swivel around that geometry. Okay, so the next thing that I'm going to do now that we've reached this point where we've completed a fair bit of our script is I'm going to get you to save at this point. So let's go File and then Save Document. And I'm going to call this tutorial, or I might call this Grasshopper Tutorial Part 2 Spiral Pavilion, and hit Enter. What's going to be great about this, again, just to reiterate this, is that now every single time that we plug something in, or if we place another component, it's going to autosave this Grasshopper file. So if we go File, Special Folders, and then Autosave Folder, it's going to create an autosave of this, which it's just created for me right now. So every time you do something, it's going to autosave. So if it ends up crashing, fingers crossed it doesn't, then at least you're going to have an autosave of what we've done. Okay, so now that we've got our first piece of geometry here, which is the base of our pavilion, I'm actually going to bake this out so that it's going to be inside our Rhino file and we can visualize it. So I'm just going to minimize our Grasshopper panel over here, and I'm going to delete the current layers because I'm going to start making my own. And the first one that I'll call is the pavilion base. And I might make it a dark gray color. And then I'll set it to be the current or active layer here, so that now when we go to our panel over here and we select our solid union, I can right click on this canvas and it'll automatically bake it out into that layer, and you'll be able to see it like that. Now what I can do is I can turn off the preview of everything here, and we've got this baked out into Rhino, which is going to be a really useful reference for the next part that we're modeling. And the next part that we are going to model is going to be the spiral structure itself. So what we might do is copy out the name here, pressing Control C, and then paste it back in, pressing Control V. And this is going to be part 3, spiral. And maybe we'll move down to a purple hue instead of being a blue one. Like this. And as a general note as well, it's important that we go from left-hand side to right-hand side as we're writing these scripts. So I might start this one over here so that you can read through the different steps and make it as legible as what we possibly can, and as easy to follow the logic of this as what we possibly can. So for this spiral, what I'm going to do is that I'm actually going to start making our pavilion, the pavilion spiral, at the base point that we've started here. And I'm going to do this by creating a circle, like so. So the circle asks for what our base point will be, and that will be our original constructed point in the very center, and also a radius, which maybe I might make 45 millimeters, like so, and I can plug this into here. And then I'll drag this down to the spiral part of our script. Now you can't see this at the moment, but if I was to hide the pavilion's base, then you'll see that there's this circle that is here. Maybe we can go to ghosted view so that we can actually see this. Now, you'll have to bear with me for 5 minutes whilst we go through the steps for creating this spiral structure. Just follow along. So the first thing that I'm going to do is that I'm actually going to take what's referred to as the end points of this curve. So if I had a curve that looked like this, and I was to reference it into Grasshopper by making a curve component and setting this one curve, I can use this particular component called end points. And this will give me the start and the end point of this curve, which I can then use a point container or a geometry container to see which one is which. Again, geometry, you can put any type of geometry inside, so curves or surfaces or polysurfaces, whatever you sort of want to. And with this circle component, what I want is I want one of the points on the curve itself, so I'm going to use this end point component here. And because it's circular, you can see that the start and the end point are going to be exactly the same, but it's just useful to get a point along the curve itself. And with this, what we're going to do is that we're going to create a range of points that actually spiral around and upwards. So the first part of this is getting all of these points to move upwards, like in the Z direction. So what we're going to do is use that move component that I introduced you to earlier, and we're going to move the start point upwards, and you can see that by default it's moved it upwards. So if I wanted to, I could move it up by, let's say, 90 millimeters. If I plug this straight into motion, it's going to turn red, and the reason that this is because we haven't given it a direction. So we need to again give it that vector, and we're going to use a unit Z vector, which again means that it's moving upwards in that Z axis. And I'll plug 90 into the factor, so it's going to move it 90 units upwards, like this. But for the purpose of this exercise, I need a whole range of different points to start spiraling around. I might need maybe like over 100 points, in fact, to because I'm going to turn all of the path of these points into a curve itself. So to do this, we're going to use that series component again. Series, as you may remember, lets you set a count. So in this case, maybe we'll make it 180. And then we can, to visualize this, we could use a panel to see what's happening here. And basically, this is just counting from 0 all the way up to 0 to 180. It actually goes to 179 because when it includes 180, starting from the point 0, it only counts up to 179. If we were to start it from 1, it would go all the way up to 180. And what we're going to use this for is we are going to move our series component over here. And you'll see that there's an option here called step size. So if we get a panel once more, I can show you that if we made our step size 2, then it would count in increments of 2. So 2, 4, 6, 8, 10, 12. If we were to make it 10, you could see that it goes 90, 100, 110, etc. And so what we're going to do here is that we're going to move these points upwards to 90, but I'm going to divide the increments up. So follow along with me now. Let's go division. And we're going to take our 180 value, which is the number of points we want, and we're going to divide it by how far you want each of these points to go. And then this is what we are going to set for our step size. And then 90 is what we're going to use for the count. And then we can replace, instead of having 90 here, we can replace that series component with our unit Z component over here. Maybe I'll move this downwards like this. We can move this a little bit further down, just so that it stays organized and that you can read through it really easily. And so now what we can see if we hover over this is that we've got 90 values. So if we take this and group it, we can label this as number of points in spiral. And then this 180 value is the height of spiral. So this will let us make it taller, and this will increase or decrease the number of points that are in the spiral itself. But I'm going to use the values of 180 and 90 for the time being. I also want to keep this as organized as what I possibly can, so maybe I'll move this down here and I'll say that this is setting the spiral height and point count. And then this is the spiral circumference. Okay. The next thing that we're going to do is that we're going to start rotating each of these around the spiral itself. And to do this, we're going to use a rotate component here. And what we are going to rotate is this geometry here. You can see by default that it's rotating all of this exactly the same amount. So what we're going to do instead of this is that we are going to take our number of points here, and we're going to use another series component. So again, this will be the count that we use, but in this case, we're going to use a completely different step size. So what we might plug in here is we could start with like 0.3, for example, and set this as our step size. And it's always good to use relays like this to keep your script being as organized as possible. And I'm going to plug this into our angle, like so. And the last thing that I want to do is that I'll make another relay up here, because this is going to take our original constructed point. So I'll double click over here to make this relay, and then I can bring this down over to here, to this plane. And then I might start making a couple more relays as well. So this one can go over here, and then this one can go down here like this. And so now what's happening is that this is setting the amount of rotations. It's a little bit difficult to visualize this at the moment, so what we can finally do is we can use something called interpolate, which is a way of creating what's referred to as an interpolated curve. So there are a few ways of making curves. If you hit Control-Alt on your keyboard and then click on this, you'll see all of these different curve options. So we could create lines between 2 points, or we've already used circles, or ellipses are created in the same way. You could also use these different spline options. So for example, polyline will create a polyline through a set of vertices like this, but you can see if you zoom in that these are actually straight sections. Whereas what we want to use is an interpolated curve, which is going to let us create a smooth, bendy curve through all of these points, like so. And then we can turn the preview of this off, and we might turn the preview of all of this off as well. And now you can see that we've got this bendy curve, and as we add extra value to this rotation amount, then it's going to create more or less spirals around for our pavilion. The other thing that I'll note for this rotate component, which you should be wary of, is that by default, the rotation isn't actually in degrees. It's in a unit called radians. If you wanted to rotate something by 45 degrees, what you would need to do is we would take our rotate command, and then we would put in 45, like so. And yeah, just something to be wary that you would need to right click here and set it to degrees instead of radians. Just something to keep in mind about that component itself. But for the purpose of what we're doing, it's absolutely fine because we're getting the result that we actually want to already. The final thing that I'm going to do here is that I'm going to take all of everything that we've done so far over here, and I'm going to move it upwards like this. And I'm going to create a group, and I'm going to make it purple, but a little bit less saturated. And this is just going to help with the grouping of this part of our pavilion. Actually, maybe I'll delete this relay and I'll pop this down here like so. Great, now we've got the spiral part of our pavilion. Okay, so the next thing that we're going to do is that we're going to turn this spiral into an actual walkway that you can walk up. And the way that we are going to do this is that we're going to take the points from our rotation here. So I'm going to use a points container that we can see going around. And this is what we're going to use to start to craft our walkway. I might also take this group name, and I'll put this over here, and we can call this 4.walkway. Maybe we might go to a pink color now. What we're now going to do is that I want to offset all of these points so that they're offset over to here, so that we've effectively got like an offset curve, and then we can loft between all of these curves that run through. The way that I'm going to do this is that I'm going to scale all of these points outwards. So what we could do is that we could create a scale component from here, and we can plug all of our points in like this, and maybe we might scale it out by a factor of 1.8. However, as you can see at the moment, what's occurring here is that it's scaling the entire thing. So it's scaling upwards as well, whereas what we really want is only for it to scale outwards. If we were doing this inside of Rhino itself, the command that we would use for this is scale one direction or scale 1D. But there is also a command for this inside of Grasshopper itself, and this is called scale NU. You'll see that this comes up whenever you type in scale. It's great. You can sort of just search for components based on what you think that the words might actually be. So scale NU. And what this will let us do is that we can take our original points here and we can scale it in the X direction and the Y direction, but not the Z direction. So this means scale it out this way and scale it out this way, but not scale it out upwards. So when we plug this in, you can see that this is scaling it outwards like this. And what we're going to do with this is that we're actually going to create a line between these two sets of points. So we can use the line component. Make sure that you don't take the container. We want to take this one here, which will prompt us for a start point and an end point for this line, like so. And now what we can do is we can turn the preview of all of this off, and you'll be left with all of these lines that go through like this, which we can then loft. But before we do that, I'm going to create a group here, and we'll call this create walkway path. And I'm also going to move it into a particular position. This will all make sense later on. I'm just going to take these lines that we've created, and I'm going to move them downwards. So I'm going to create a motion in the Z direction. And then I'm going to move it by 8. So 8 units. You'll see at the moment though that when we plug this in, it'll actually move it upwards. Whereas what I wanted to do instead is to move it downwards. So what we can use here is a component called negative, and this will turn all of our values negative. And now it's moving all of these down. And we can group this and call it move downwards. And I'll turn the preview of everything but the last part off. This will make sense in a little while because it's going to affect the arrangement of the different elements of our pavilion. Now, the next thing that I could do if I wanted to is that I could loft between all of these curves like this. But I'm not actually going to do that just yet. What I want to do is I want to show you how you can actually shatter all of these curves. It can be a really useful command in the future, and delete maybe the ends of this. To do this, we can use a component called shatter, like this. And we can plug our curves in. And what shatter does is that it will actually break this curve into 2 parts. So if I was to, for example, reference in maybe 20 millimeters, so 20 units like this, you'll see that it'll come up saying that it's failed, and the reason that it's probably failed is because these probably aren't 20 millimeters long. So let's see how long we can make these. So what I'm going to do is that I'm going to shatter it at 30% of its length. So I'm going to put in a slider value of 0.3 and then plug this in. However, the other thing that I want you to note is that when I plug in 0.3, it's going to evaluate it at 0.3 millimeters. So what we can do instead is that we can right click on this and say reparameterize. And what reparameterize does with anything that evaluates a curve is that it actually breaks it down into percentage terms. So now it's going to shatter that at 30%. So if I right click here and say bake, what we'll see is that we've got 2 parts to this curve now. So it's actually shattered it at 0.3 or 30% of the overall length. Now, I've shown you that when I baked this out, that it's broken up at 30%, but what we actually want here, we only want the first part of the curve, not the second part of the curve. So what we can do is we can use a panel to look at what all of this data looks like. And you'll see that on this list, it's automatically put each of our curves onto its own branch. So you can see that if I bake this out, this part of the curve here is item 0 on this list probably, and then this part here is item 1 on this list. And you'll see that this arrangement will continue out. So what we can use is a list item component here. Let's take item 1. So that's item 1 on this list, item 1 on this list, and item 1 on this list. And we can use another panel to see what this looks like. And now it's only going to be taking this part of each of our curves. I'm going to do a much more in-depth overview of list structures and controlling data structures a little bit later on, but I'm slowly introducing to you how we can actually use all of these data structures before I take you through this. Now, the next thing that I'm going to do is that I'm going to begin lofting between all of these curves. But you'll see that when I use a loft command like this, that it's going to turn up red and it's going to say loft could not be constructed. The reason that this is happening is because if we use that panel again, what this loft is trying to do is it's trying to make a loft from each of these curves individually. So effectively in Rhino, it would be like selecting this curve, typing in loft, and then only referencing one curve, so it can't create a surface from it. If we wanted to do all of these curves together, what we need to do is flatten this list, like I showed you earlier, so that all of them are on the same branch. And now what you'll see is that it'll loft between all of these different elements. So this is what flattening a list does. It means that all of these elements are going to be computed together in the same way as we did this with our solid union earlier. I'm now going to group all of these parts together. And I'm also going to say here, remove inner section of walkway, because this will affect how much of the inner section of our walkway we remove. And then I'm going to call this the same as this overall. And then I can move this over to here, and I might move this downwards just so that we've got a reference of it. And I'm finally going to go back to all of this, and I can turn the preview of all of that off, and I can undo inside of Rhino our bake so that we don't have all of those lines. Now, the next thing that I'm going to do is that I'm actually going to turn all of this surface, so this is a loft or a poly surface, and I'm going to turn it into a mesh. And the reason that I'm going to do this is that mesh geometry is actually much more efficient than what NURBS geometry is. So it's much more efficient than surfaces or poly surfaces or sub-Ds in terms of the size of your file, but also in terms of how long it takes for things to compute. The easiest way for you to turn something into a mesh is that you can type in mesh brep here. And what this does is that it just takes any brep and instantly turns it into a mesh. You'll see that there are a whole bunch of settings here. We could say mesh settings. And you can use this settings custom, and you can set a whole bunch of important little aspects to it. So like the minimum number of quads in your mesh, or maximum angles for between the different vertices and edges. But that's more advanced than we really need to go into detail with at the moment. It can be really useful if you wanted to be very controlled with it in the future. Generally speaking, mesh brep does a really efficient job of turning any of these into quite an efficient mesh without overcomplicating the geometry. Moving on from this, I want to show you a general principle as well about how we can model with meshes from scratch rather than creating meshes and then modeling with it. So the first thing that I'm going to show you to do here is actually to create pipes, which are meshes. So if we were to reference in a curve like this, where it says curve, and then I was to say set one curve, and we could create a pipe, and maybe I'll set that radius to 5, like so. This doesn't seem particularly heavy at the moment, but inside of Grasshopper, we might be making facade paneling systems that might have 10,000 or 100,000 of these individual curves, and you'll see that makes your model much slower to run, and also the files will be much larger. And so if ever you're modeling pipes, or if ever you're modeling lofts or anything like that, I'd encourage you to create meshes from scratch. And one component that we can use is called mesh pipe. It's either this one here or this one here. I personally prefer mesh pipe from here because it gives you quite a few options. This is a part of a plugin called Nursery, which you can download from Rhino. It's on the list of plugins that I've given you for this tutorial, and it's also a part of that zip file if you're following along on my courses website rather than YouTube. And what we can do is we can plug this curve in here, and we might set that radius to 5 like we had it earlier. And it gives you a few other settings. So the difference between meshes and NURBS geometry is that meshes are made up of either quad, so 4-sided faces, or triangles, individual sided faces, rather than being mathematically defined. So you don't have smooth edges to it. You've got individual planarized faces. And there are a few options that we can make here. Firstly, we can affect the number of sides. So see on this mesh, if I was to bake it out, you'll see that it's got a square at the end. When you change the number of sides, so if I was to set it to 10, what this does is that it makes it much more smoothed off. See how it's going from 4 to 5 to 6 sides? And if we were to set 10, then it's going to make it look much, much rounder. To give you a preview of what this looks like, I can show you here. See how it's got a much rounder edge to it? So that's what changing the number of sides does. The other thing that you can do is that you can change the number of sections. So if I was to set 3 sections like this, then what it's going to do is that it's only going to change direction 3 times. So 1, 2, 3, like so, but we could make that 10 or even more, and it's going to start to smooth all of this off. And so this is probably going to run 1,000 times faster than if we were to use normal NURBS pipes inside of Grasshopper, which can be really, really useful if we've got heaps of them. The other things that we could do is that we could use a mesh loft component like this. And what this can help us do is that if we've got all of these, let's say that we've got a couple of polylines like this, and we were to reference these in as curves, set multiple curves, then we can plug this in, and it asks whether we want to cap the ends of this. By default, this will say yes. What this means is that it would sort of like close the shape off by putting a cap at the end, so it would make it a closed shape. And we can use something called a Boolean toggle. And what this lets us do is set yes, no, or true and false values like this. And we can plug in false here so that it doesn't cap the ends. And you're going to be able to create lofts from meshes. And when we bake that out, you can see that this is going to be a very, very efficient lofted structure. The only thing to keep in mind is that you have to make lofts with straight sections. So if I was to create bendy curves like this and try to loft between them, like so, if I was to set these curves, then this loft isn't going to work. It only works for straight section curves like that because all meshes have to be made up of straight sections faces. So any geometry, if you're making heaps and heaps of it, make sure that you model it with mesh geometry right from the start. And this is to a degree what we're doing over here. Now, the next thing that I want to introduce you to is an idea of topology. So topology is the makeup of all of these faces. The point of me introducing topology to you for this is that we're going to use a component here called Quad Remesh, which is built into Grasshopper itself. And what this allows us to do is that we can plug in our mesh brep over here, so this geometry, and I'll turn the preview off of this, and you can see that it actually breaks the faces up into quad faces, so square faces like this, and it makes all of these sections relatively clean, so even face sizes like so. It's a really, really useful component to know. And this will come in really, really handy because the next step that we're going to do is that we're going to offset this mesh. There's a really powerful mesh editing tool inside of Grasshopper, but you have to download it as a plugin. It's called Weaverbird. It installs differently to what other plugins do. So you actually have to go to this download website and you can download this Weaverbird for Rhino 6 or 7 and you just need to run this component. What we're going to do is drag this into Grasshopper itself like this. Rhino will then use what's referred to as the package manager to actually download it and install it for you. You just need to click install. I'm not going to have this come up because I've already got it installed, but when you're prompted with the package manager, just press install and then Weaverbird will start working, and it gives you some example files here of how you can use it. So now when we go back to what we're doing, you'll be able to use Weaverbird's built-in mesh editing tools. And the one that I want to use is Weaverbird Thicken Mesh. So you can type in Thicken Mesh, and it's this one here, Weaverbird's Mesh Thicken. And we can plug in our mesh here and we can offset it by a particular distance. So I might offset this walkway by 4.5 millimeters. And you'll see that all of a sudden this shape becomes three-dimensional. You'll notice though that it's actually offsetting downwards. And I want to show you a way of actually fixing this. What we can do is that we can flip the faces of any mesh because every mesh has what's referred to as a normal direction. So it's a direction that the faces are facing. And what we can do is we can use a component called flip mesh like this. And when we plug this into here, and then we can plug this over here, and then it changes the directions of those faces. So now it's going to offset in the other direction, like so. So I'm going to set this at 4.5. And then the next thing that we're able to do is that we can use something called Kappa-Clark subdivision. So you've got all of these different subdivision tools here. This one here called Kappa-Clark subdivision is, I think, the most useful in this scenario. It's just going to smooth off these edges. So if we type in cat M, it'll come up. And I'm going to select this one. And we can plug it straight into here. If we then turn the preview off of these previous sections, then you're going to be able to see our smoothed off mesh like this. So it's starting to smooth off those edges. The other option that you have for this is that you can set the level of subdivisions. By default, it's 1. So if we were to set it to 2, then what it's going to do is that it's going to add more detail to these faces. So if we bake this out, you can probably see it a little bit better. I'm going to make sure that it actually bakes onto our default layer rather than our Pavilion base layer so that it doesn't appear black. And you can see that it's got way more meshes than if I press Ctrl Z to unbake that and I go back to our original Weaverbird thicken and I exit out of here. See how it's got way more faces than this original one? And so what I'm going to do now is that I can move this over here and I'm going to group this and label it as well. And we're going to call this thicken walkway. So thicken walkway. And this is the final part for our walkway. So I'm going to take all of this and group it together and I'm going to make this pink. And I'll move the walkway label down here. Now that we've made our walkway, what I'm going to do is bake this out. So I'm going to make a new layer and we'll call this walkway. And I'll make it the active layer and we can go to Grasshopper. And I'll show you again that if we go to our end mesh component here, instead of clicking on the canvas, if we click on the component this time and we'll say bake, and then it'll prompt us about which layer that you want it to bake onto, which is different from the way that we baked it last time. So I'm going to select walkway and then I'm going to click OK. And you'll see that this will bake all of this out now. So it's physically inside of Rhino and I can edit it there. Now I've made this so that we've got a walkway that we can walk up, but obviously as you walk up this walkway, there's no handrail, so it's going to be like super easy for someone to fall off. So that's what we're going to make next. We're going to make a handrail and it's going to show you a whole lot of really useful parametric logic here. So let's make another title and we'll call this 5 handrail. And press OK. And then I'm going to change the color of this so that it's red. Cool. Okay, so the first thing that we're going to start off with is we're going to take our original curves, which were over here. So it's just before we feed it into the loft. And I'm going to make a curve container. And I'm going to plug it in here so that we can take all of these curves that run up our geometry like this. And I'm going to feed it over here. And what I want to do is that I want to make a handrail, but I don't want it to start at these ends. So I don't want to loft it all the way out to here. I want it to be a little bit brought inwards, like scaled a little bit downwards. And so what I can do is that I can scale by using the scale tool. And I want to scale all of these curves individually. But as you can see, when we scale this by, let's say, a factor of by 0.5, like this, that it's scaled it all down uniformly. So it's scaled it towards the center point, and that's because the center of our scaling is automatically defined as right in the center here. And so what we want to do instead is that we want each of these to scale individually from the center of this curve. And the way that we're going to do this is find the center of each of these curves. This can be done using a component that's similar to shatter. It's a component called evaluate curve, which you can find if you type in eval curve. And I'll hit OK. And I'll grab it here and move it over to here. And what I'm going to do is I'm going to assess it at 0.5 or 50% of its length. See how at the moment, this is what I was talking about earlier, that it's not actually at half its length. What's happening now is that it's evaluating it based on distance. And so to evaluate these curves at half their length, I need to right click and say reparameterize. And now it's going to be evaluating it instead of at the actual millimeter distances, it's going to be evaluating it in percentage terms. So 0.5 being 50% of that curve's distance. And now each of these points are what we can use to scale each of these curves, and you'll find that it's going to scale each of them now individually. And the reason that this is happening is because there is an alignment of data. So we can take all of our curves and plug this into a panel, and we can take each of these points and plug it into a panel. And there is an alignment of data between each of these lists. So now item 0 on this list aligns with item 0 on this list. Item 1 on this list, being the first curve, aligns with item 1 on this list, being the first point. And this is how data structures work inside of Grasshopper. This is quite a simple example. We'll go through a lot more sophisticated workflows in the future. I'm going to group this together and we'll call this offset handrail inwards. And we'll call this handrail width, because this is going to affect the width of our handrails. Now, the next thing that I'm going to do is see by default, we've got all of these curves that come all the way out to here. So our handrail is actually going to overshoot our walkway itself. And so to do this, we're going to use a list component called Cull index. And what you might remember is that Cull index will actually cull one item off a list. In this case, we wanted to cull item 0, which is the first item on that list. So if we use a panel, we can see we want it to cull item 0. However, you'll find that potentially it's not actually culling this item here, because this is the end of the list, not the start of the list. So the next list transformation I'm going to introduce you to is something called reverse list. And what we can do, or how we can use this, is that we can right click on any of this data and we can say reverse. And now what's happening is you'll see that this isn't included. The way that reverse list works is if we take a series component and have a look at what comes out in a panel. So this is just numbers 1 through to 10, or items 0 through to 9. So there's 10 numbers. If we right click here and say reverse, then it's going to reverse the order of all of these numbers on the list. So instead of going 0 to 9, it's going to go 9 to 0. And a similar thing is happening here, where it's reversing this list outwards, and it's culling the first thing on the list, which is this one, but it's keeping all of the rest of these. And so this is what we can now use for our loft. And if we hide this and hide our mesh over here, you'll be able to see that it creates a loft through all of this. And what we're going to use this for is that now that we've created this loft surface all the way through, I want to take the edges of this. If we were to do this inside of Rhino itself, we could use a command called duplicate border. But in Grasshopper, what we can do is that we can just take a curve component, and this will automatically turn this from a surface into the curved edges. So you can feed any surface into a curve component and it will automatically give you the curve edges, even though it's just a container. We can create a group here as well. We'll say that this reduces length of handrail, so to not extend past the end of the walkway. And then the next thing that we're going to do is that if we bake this curve out, you'll see that it's actually all joined together. So we're going to use a component called explode, and this is going to explode this curve. So when we bake this now, you'll see that it's all in different pieces. And the reason that I'm doing this is because this curve that I've just made, which you can see better if I was to turn the preview of these curves here off. So only our loft and our exploded curve is visible. I'm going to use these curves here, so the curved edges, to be where our handrail is actually created. And what I don't want is I don't want it down the bottom here to start making a handrail at the start of our walkway. I know that this isn't currently at exactly the ground level, but we'll deal with that a little bit later. The point is that I don't want a handrail to start here. And so what I can do is that I can use that component Cull index. And I can find where on the list this curve actually is. So see here, if I was to say item 0, it's going to delete the curve that runs along this side. But if we say item 1 happens to be this curve here. So again, if we use this panel tool, what we're doing here is that we're culling either item 0 or item 1, or we could cull item 2 or item 3. And what this is doing is that it's removing any of those items from this list. Now, after this, I'm going to group all of this together, and we can make this be called remove rail curve at the start of the walkway. And the next thing I'm going to do is set the distance between the balusters for this railing, and I'm going to do this with a divide length component. So divide length is one of the ways to divide your curves up. You can either divide by a particular number. So if I was to use divide curve and I was to plug these curves in, then I could say I want maybe 100 divisions. But the issue with this is that it divides each of these curves 100 times, which means that this curve over here will have way more points than what these will. And so what I want to use instead is a divide length component here, which is going to create divisions at particular lengths. And the length that I might set might be like 4 millimeters. And now you can see that this spread is much more even between those two different curve types. Now we can start extruding all of these upwards to create railings. And so what I'm going to do here is that I can say that I wanted to create a line. There are a few ways of creating lines. So the one that we did before was a line between 2 points. Or what we're going to use here is actually called line SDL. And this will let us use a vector being a direction of travel and also a length, as well as a starting point to actually create our line. So if we plug this into our points, and then our direction would be our unit Z, meaning that we're going to be going upwards. And then our length can be 10 millimeters, like this. And now you can see that it's creating that line directly upwards. And so I might want to start grouping these together again. This can be called set distance between balusters. And then this can be called set handrail height. And then the next thing that we're going to start doing is that we're going to start creating solids from this. Again, I told you that we could create a pipe geometry like this, but this is going to make our file a lot larger. So what I want to do instead is use that mesh pipe component. And I'll plug our curves into here. At the moment, this is way too thick, so I might set the thickness at 0.4 for the radius. And then the last thing that I want to do is that I actually want to create a pipe, a mesh pipe, that runs along all of these edges along here. And so what I might do to achieve this is that I can go back to all of these edges here, and I can say that I want to take these curves that run along here. And so these are the curves that run along the outside. And then what I might do is create a mesh pipe that runs along these curves. The only thing will be that would need heaps and heaps of sections, and it would be quite complicated to actually set this. So instead of using mesh pipe, what I might do is I'll just use the pipe component here, because there's only 3 curves here, whereas in this case there are 912 individual curves in this list, and so this is going to make our pipe much more efficient, whereas for this it's probably okay to use a curve since there's only 3 curves in this. I'm going to set the radius as the same value as what our other radius was, but you can see that this currently isn't at the right height, and so what I'm going to do is that I'm going to take our movement of 10 units upwards, and I'm going to say move, and I'm going to move these original curves, and I'm going to move them up, and I'm going to move it by that factor of 10. So if we plug this into here, and then we might like to create a relay so that it stays relatively clean, and we're going to move it up the same amount, and then this is what we're going to plug into our pipe. So you'll see that the pipe will be generated up the top, and this is what we're going to use for our handrail. So what I might do here is I can create a geometry container, and then put these 2 pieces of geometry in here by dragging this wire, and then I'll start dragging this one and hold shift so that I can put 2 pieces of geometry into here, and then I can group this part here, and I can save this as handrail thickness. And what I might do now is that I can take all of this geometry here, or all of these components, and I'll group them together, and I'll make them that red color that we started off with. I'm also going to make sure that I turn the preview of all of this off. And then what I might do is I'll make another layer here, and we'll call this handrail. And then I can bake this into our handrail. I can bake this into our handrail layer by zooming in, selecting this geometry, and then clicking bake. And now, when I exit out of Grasshopper, and you don't have to worry about it actually exiting your file, because that's not how this works, but we can type in show, and all of this pathway will turn up again. And now you will have your walkway with a railing that goes along the edges. And you'll see that this railing doesn't start. It's not started down the end here. And up the top, it doesn't extend past the end of the walkway. It's not perfect in terms of it not reaching that length, but you've got a pretty good grasp of the principles of how this works. You can imagine that if you were to create this manually inside of Rhino, it would take you absolutely ages, and so this is an example of how you can create lots of geometry very quickly by scripting it inside of Grasshopper. Now, the next part of this is that currently it looks like this walkway is floating. If you wanted to create a walkway like this in real life, you'd have to use some pretty superhuman materials. It'd be very thick steel, or maybe if it was super lightweight and rigid, you could do it out of carbon fiber, but it'd probably never be built because that would be so expensive. And so what we're going to start doing now is that we're going to start implementing some structure into this, which will hold this and stop engineers from fainting if you were to actually show this to them. So I'm going to do this in 3 parts, which will look like this. Firstly, we're going to create this hexagonal cell structure that runs up around our actual walkway like this. Second, we're going to create a column between this that holds and supports that structure that runs upwards, like so. And then the last thing that we're going to do is that we're going to create these beams that come out and they actually support the walkway itself as a connection between these 2 structures. So there's going to be 3 parts to this. So to get started, what we're going to do is let's take our handrail label over here, and I'm going to bring this down to the end, and we can relabel this as 6 hexagonal cell structure. And maybe I'll make this orange instead of red, so we can visually differentiate it. And after this, what I'm going to do is I'm going to go back all the way to our spiral part of the script, and towards the end when we created this interpolated curve, and what I'm going to do is I'm going to drag it downwards to here, and then I might add a relay here so that it stays clean, and then I'm going to drag it back over to this hexagonal cell part, because this is what we're going to use as the input for this part of the script. And I'm also going to turn the preview off for these parts over here, so I can say preview off. So to show you what this looks like, it's this curve that runs along, or it's this original spiral curve that we had that ran along like that. And what we're going to do with this is that we're going to take the curve and we're going to extrude it downwards. So I can use the extrude command, which I showed you earlier. And what I'm going to do here is that I'm going to extrude it in the Z direction, so upwards or downwards. And in this case, I'm going to set it downwards, so we'll say negative. And I'm going to extrude it downwards by, let's say, 21 millimeters. And so now we've got this surface that runs all the way around here, like I showed you earlier. And what I want to do following this is that I want to panel this surface. I want to give it a hexagonal grid. And what we're going to use for this is a plugin called Lunchbox. And Lunchbox specifically has a whole range of different panelization methods. So you could create diamond panels on a surface, hexagonal, quad, skewed, triangulated, a whole range of different paneling types. The ones we're going to use for this are hexagonal cells. And when we plug it in, you'll see that it doesn't quite work so well. And the reason that this is because it's got a default number of divisions in here. So it's 10 by 10, whereas in reality, the U divisions, which run upwards and downwards, we can probably set it maybe 5. And because this is a very, very long surface, we could set the V divisions, which are the ones that run along the curve like this and spiral, at a much larger value, so maybe 175. And you'll see now that this starts to create all of this diamond webbing shape that runs along here. And now we can take all of this and we can group it all together. And these are going to be our hexagonal cell structures. I'm going to show you how to turn this into solids a little bit later in this scripting process. But for now, let's just make a color for our grouping. And we can leave it like that. And maybe we'll turn the preview of all of this off for the time being as well. Now, the next part of this script is that we're going to create that central column. So I'm going to copy this name down here, and we can call this 7.central column. And I'm going to make this yellow instead of being orange. And to start this central column, what we need is a starting point, and I'm actually going to go all the way back to the start of our script here. And I'm going to create a point like this so that it links, if I hide this, it links this starting point, so the 0, 0 point that we started with, and I'm going to bring it all the way back to our central column part here. I showed you earlier that with these wires, you can actually right click on those wires, and we're going to say wire display hidden. And it's going to stop the wire from going all the way across and messing up our entire script because it's lovely and clean now. And what we're going to do is that we are going to create a line that's roughly the same height, which is going to act as our column. And so we can say line SDL, like I showed you how to use earlier. So we just need to set the start point, which is here, and then the direction, which is the unit Z direction, which you can achieve just by typing in Z, and then a length, so maybe 185 or 184 millimeters roughly. Let's just set that. And now we've got this column that runs all the way down the center. Now the next thing that I want to do is that I want to create a whole bunch of connections that go out to our structural grid. So all these hexagonal cells, I want our column to actually connect to those hexagonal cells. And the way that I'm going to do this is that I'm going to take our line here and I'm going to divide that line up using the divide curve component. I'll just plug this into here and then I'll set the count at maybe 16 connections. And so now all of these points that I'm generating across this curve are I'm going to find the closest points on this hexagonal grid. And the way that I'm going to connect these is I could use a component called closest point. So this works in the same way as that curve closest point worked that we used when we were going through the attractor logic. But instead of that, I might use something else because I'm trying to show you as many components as we can. I'm going to use a component called pull point, which is actually more efficient. So this is going to allow you to pull your points to a range of different geometries. And what I'm going to pull it to is the centers of all of these hexagons. So if I type in point like this, then it's going to give us all of the centers of these hexagons. And I can say that I want to pull these points to this. And then I want to create a line between these. So I want to create a line from this start point here to this closest point here. And see how now it's connecting outwards? So it's connecting between these parts of this curve, and then it's connecting to the closest hexagonal points along here. Now, to make this into a solid shape, what I'm going to use is something called multi-pipe. And multi-pipe is like a pipe, but it creates smooth connections between multiple sets of curves. And so what I can do here is that I just need to break this curve in particular into multiple curves at each of these points here. And so to do that, what I can say is I can say shatter, because I want to shatter this curve into multiple parts. And then I can take our divide curve parameters. So these are going to be the distances at which we actually divide this curve upwards. And I'm going to put this into the parameters here. So now when I bake this out, you'll see that it'll be one curve here, and one curve here. So it's shattered it at each of these intervals, because that's what these parameters represent. And then I can feed both of these into our multi-pipe. So if I type in multi-pipe, it's built into Grasshopper, I believe. And I'm going to take our shattered curve here, and then our lines here, and then I'm going to make the node size a whole lot larger. So I can set this at maybe 3.4 millimeters, so that it's a much thicker column, like this. Now, the next thing that I want to do is, because this isn't connecting these up very evenly, what I want to do is I want to make sure that these are all on the same list. And you can see here that there's actually a data structure to this. So there's 17 items. When it says n equals 17, that means there's 17 items on the first branch. And then under that, it says n equals 16. So there's 16 items on the second branch. Again, we're going to go through this in a lot more detail a little bit later on, and you'll feel a lot more comfortable with it. But for now, what we're going to do is just flatten this. And you'll see that now it treats all of these like they're all together on one list. And it's completely changed this up, and it's starting to multi-pipe this out. Now there's two more things that I want to do. One is that I want to label all of this. So I'm going to group this together here. And then I will group this together as well. And I can set this as number of connections, just so that we know what this actually represents. Maybe I'll group all of this together, and this can be the column height, just so that it all makes sense. when you come to revisit this. And I can, and then I'm going to pull this point component over here to make it a little bit cleaner, and I might add a relay like this, and then I'll drag all of this outwards like here, over to here, and that over to there, and then we can group all of this together. So Control G, and then I'll change the color of this to be a little bit yellow as well. So now we've got this central column that runs upwards, and we've also got our hexagonal grid. Okay, so the last part of this is creating that structure that comes out and actually supports the walkway itself. And we're also going to take our hexagonal cells and make them three-dimensional. The way that we're going to do this is with a multi-pipe, like we did last time. And so what I'm going to do is type in multi-pipe. And I'm going to put in the hexagonal cells into these curves first. And maybe we can set a node size as 1 millimeter, like this. And it'll create all of this as one interconnected multi-pipe system. I'm going to move this further down the end, because this will actually go after all of our structural connections to the walkway itself. But we can also plug those walkway connections into the same multi-pipe. And what I'm going to do is that I'll copy this name over, and we can start this over here, and we'll call this walkway supports. Maybe I might make this part of the script green. And then I might also copy this down, just because I'll put all of the pipe construction together as well, and we'll label this section, and we can call this 9.pipe. Maybe I'll call it multi-pipe curves. We'll press OK, and then we can change the color of this from green to blue, because this will be the last color that we actually set. Okay, so to start our walkway supports, what I'm actually going to do is I'm going to make my way back. I'm going to make our way to this pink part here. And on this list item, I'm actually going to take all of these curves that we had. So where it said removed intersection of walkway, and these curves were the curves that went across like this. I'm going to take these curves, and I'm going to create a relay that runs along the top so that it can look nice and refined and clean for our script. And I'm going to drag these back out over to here. And this is what we're going to use for the input of our walkway supports. What I want to do with this is that I want to find the center of all of these curves again. So to do this, as you're aware, actually I might move this multi-pipe downwards as well, just because we're going to deal with all of this at the end. And so to do this, what we're going to do is type in evaluate curve, or eval curve. We'll have it come up. And I'm going to evaluate it in its center point, so 0.5, because this is where we're going to connect it to, or connect our supports to. And don't forget that you need to make sure that you've got reparameterize turned on, so that it reparameterizes it into percentage terms rather than distance parameters. Then we're going to take all of our points that run along here, and we're going to use the interpolate curve command, like this. And the final thing that I'm going to do is that I'm going to move this downwards, because this is going to be where a part of where our structure actually connects. So what I might do is that I'll say move, and then move it in the Z direction again, and move it in a negative amount, and maybe we can move it downwards by 5. We can plug this into here, and now it's going to move down by 5 like so. So I'll group this all together again. Say move down. And this part here will be the curve to connect structure. Okay, for the next part, I'm going to go back to our spirals here, and we're going to take this interpolated curve. We've already got a relay that runs along the bottom, so I can actually use this relay so that I don't have to create multiple others. And I can name this relay by right-clicking and saying spiral curve, and then plug it into a curve component like this. Maybe make another relay, just to keep it quite organized. And what I want to do with this, so this curve here currently runs along the top of this hexagonal structure, and what I want to do is move it down to the bottom of the hexagonal structure. So I'm going to say move, and then the amount that we're going to move it will be the same amount that we've offset this hexagonal structure downwards. So we can go to hexagonal structure, and we're going to take this vector. So we'll use a vector container here. And then I'm going to drag this out over to here. And this is the vector that we're going to use for our motion. Now what you'll get is you'll get this original curve, which is up here, and it's going to move it to down the bottom here. And then we're going to say divide length, like this, and we're going to divide it at increments of 15. And these are going to be the positions that all of our structure actually comes out from the hexagonal grid here, and then connects over to our walkway itself. So I'm going to create a group that expresses this, and we'll call this number of connections. And then following on from this, we're going to take our moved geometry that we had over here, and I'm going to use that pull point component again. And what I'm going to do is I'm going to take this divide length, which gives me all of these points, and I'm going to pull it to this curve. So I can plug this into the points, and then this into the geometry. And what this is going to give me is it's going to take these points, and it's going to take this curve, and then it's going to find the closest points on that curve. And we're going to visualize this with the line. So if I create a line like this between here and between these points that have been pulled, like so. And see how now it's created this structure that comes off like this. Now the next thing that I want to do is that I want to actually create a line that goes directly back from here to the closest point on this hexagonal grid. So to do this, what I'm going to do is I'm going to take these hexagonal cells, which are these curves over here. So we're going to go to the end of our 6 hexagonal cell structure, and we'll take these curves like so, and then we can take them back over to here. And I'm going to take all of these points that we've got over here, and I'm going to use that component called pull point one more time. And this is the geometry that we're going to pull it to. We're going to pull it onto these curves. And this is the geometry that we're going to pull. And then we can make another line between these two components here. And so now we'll have this line that goes from the bottom to the top, and then this one that goes straight back to our hexagonal cell geometry. Now the final one the final line that we're going to create is going to be the line that connects from the tip here into our walkway structure. And to do this, instead of using this pull point and creating a line between 2 points, I'm going to take these points that we've created over here, and very simply, I'm just going to make a line that points directly upwards. So we can use that line SDL. And these are our starting points. And the direction is going to be in the Z direction. And then maybe as a length, we might use 6 mil. And now I've got a line that goes upwards like this. And it's always helpful to sort of understand what these curves actually are. So what I can do is I can create some curve components like this, and we can start to label these. So this might be called, if we right click on this component, we can change the name of it. So we'll call this curve vertical walkway beam. And then we could call this curve horizontal walkway beam. And then for the last one, we can call this the diagonal. Actually, this one here is the diagonal, so we can call this diagonal walkway beam. And then use these little align functions that I showed you earlier to make it align properly. And then what I'm also going to do, I'll take these hexagonal cells that we've got over here. So we can label this as curve hexagonal cells. And then we can bring this up to here as well. And what I'm going to do is I'm going to take these, and this is what we can include in our multi-pipe curves. So instead of having it dragged all the way from over there, what I can do is I can replace this node over here and then hold shift to add all of these extras in. Like this. And now what you'll see is that we've got all of this being multi-piped. Now there is one thing that I'm going to get you to fix up here. And if we bake this out, you'll see that this doesn't multi-pipe properly into these parts here. And that's because these curves aren't split. And so what we can actually do is that with these hexagonal cells, instead of taking the cells themselves, we might just want to take the endpoints. And to do this, we can use a really, really useful component. And this component is called discontinuity. The way that discontinuity works, and I'm showing you this now because I think it's really important to learn what this component is that if we take a curve like this, so say set one curve, and then we say discontinuity like this, and plug it in, this is actually going to give us the points that this curve changes directions. So if we go back to our hexagonal cells over here, and we plug in the hexagonal cells into discontinuity, it's actually going to give us every single point where this changes directions. And so if we pull this into our geometry that we're pulling everything towards, and just keep in mind, this is one of these times where it's important to flatten everything off. I'll go through why it's important in a few minutes. And now what we can do is that we can turn the preview of all of this stuff off. We can turn the preview of all of this stuff off, and the preview of all of this off. And what I'm going to do is I'm going to undo the bake that we did a second ago. And I can delete this curve. And I'm going to make this into one group over here. So this is going to be our multi-pipe group. I'm going to make this blue. And then I can group all of this together. And this is going to be our walkway group, so I can make this green, just to clean up our script a little bit. And then I'm going to start baking these elements out. This is the end of the central column. And I can bake out that central column. And then I can also go to this multi-pipe curves over here, and I can bake this out as well. And then I can turn the preview of all of this off. And maybe I'll save it at this point. And I can exit out of this. And now let's go to a different view. Maybe we'll go to our monochrome viewport to get a better preview of this. And so that's all of our geometry modeled for this exercise.
Okay, so the next thing that we're going to do after learning all of these geometric modeling tools is that I'm going to show you different ways to actually display it inside of Grasshopper.
Okay, so to get started with this, there are a few things that I'm going to do. Firstly, let's select all of the geometry that we baked out earlier and just delete it. And then we can go into our shaded viewport as well. And what I'm going to do is I'm going to create a group over here with all of these different geometry components. So if I type in geometry, I'm going to right click on this one and I'll rename it geometry handrail. And then I'll make another one below this and we can call this geometry, and this can be for the walkway. And then another one below it called walkway support. Then the other piece of geometry that we had was for the base. And then finally down the bottom, one for the central column. And then similar to what I've done with all the other groups, I'm going to group this together. And maybe for this final part, I might make this black. And it's just going to help having all of these together in the one place when we start connecting up all of the custom preview settings. Don't forget as well that if we drag this down and we want them all to be evenly spaced, what we can do is we can click these little things on the right hand side to have them all aligned to the right, and then this one down the bottom to have them all align evenly out like that. And then I'm going to start to connect these up. So first of all, let's find our handrail. I might actually maximize this for the time being. So our handrail was the red part of the script. And what I'm going to do is just drag the end of the red part of the script out, and I can connect it in over here. And then I'm going to create a little node for this by double clicking, a relay by double clicking over here, just so that the script stays a little bit clean. And then for our walkway, we can go back over to the pink part over here, and I'll take the output of our walkway and I can plug this in over here, and I'll make another little relay and maybe move this one up as well, just to keep it a little bit cleaner. The next part of this is our walkway support, which is just this multi-pipe that we've created over here. And then the base geometry, we can connect right back up at the start over here. In this dark blue color is our pavilion base. And then finally for our central column, this can be connected up over here to our number 7 yellow group, which is the central column that we created. And maybe I'll drag this a little bit further out. And I'll copy the name over. And we can rename this to 10.bake. Maybe I'll change the color of this to white. And make it a little bit more spaced out. Now, there are a whole range of different methods for actually displaying geometry, some of which you can bake out inside of Rhino and it'll create materials, some of which will change the colors of the geometry itself but won't actually render. I'll sort of explain the technicalities of these a little bit later, but I'm going to make it as simple as possible to actually start off with. So the first one that we're going to start off with is just called Custom Preview, which is this component here. And what Custom Preview lets us do is that we can choose any, what's referred to as like a material, but in this case we could choose a color. If we go to input up here, you'll see that there are a whole range of different ways that we can choose colors. So there's what's referred to as like a color wheel if you wanted to create multiple colors, which we won't go through. There is a color picker, which is sort of similar to the way that we were picking the colors of our groups earlier. And then the one that we're going to use for most of this is what's referred to as a color swatch. And a color swatch just lets you click on this area here and you can choose a particular color and you can input it in. And so what I'm going to do is delete these. And then I'm going to take the walkway geometry, which is the first geometry I want to bake out. And I'm going to plug it into Custom Preview because that's our geometry. And then choose this as a color. And you'll see that now it'll start displaying in this particular darker color, like so. You'll notice though that it gives you an option here to have a material instead of a color. So if you wanted to, you could actually reference in material settings. And the way that we would do this is that you can double click and type in material. And there's this option here called create material. If you wanted to find where this is, you can hold the Control and the Alt key down and then click on the component. And you'll see that it comes up under all of these different display options over here. There's also all of these different ways that you can sort of choose display modes, which you'll be familiar with if you have any knowledge of graphic design like RGB or CYMK. And it's under these different ways to preview. So we can say like custom preview, which we've used earlier, and create material, and there's a few more that we're going to go through a little bit later. But as I took you through in the Rhino video, there's a whole bunch of different options for when you create material. So diffuse is the color of a material. Specular is sort of like what color it reflects in, sort of. Emission is how much light it actually emits if it glows. Transparency is obviously just whether it's like a glass-like material that is actually transparent. And shine is exactly how reflective it is. So a shiny object would be like a mirror, and then a not very shiny object would be like a very rough rock, for example. So the next one that we're going to reference in, on the next geometry that we'll reference in, is our handrail. So we can use another custom preview here. We can plug in our material and we can plug in our geometries over here. And then we can start referencing all of these material properties in. You'll see by default it will be pink because it's referenced in hot pink. There's also a whole range of different material names that are actually referenced in, but we're just going to use our swatches. So maybe we'll choose like a black color to start off with to show how we can affect a few of these things. Specular, you can just change the color of the specular if you wanted to, so change the color of the reflections. I'm not really going to go through that. Emission, I'm not going to go through. Transparency is sort of useful, so transparency is on a scale of 0 to 1, so if you were to set it at like 0.22, you can see that it's very it becomes a lot more transparent as the numbers get larger, and as it's smaller it becomes less transparent, but I'm not going to affect that. And then shine is also given as a percentage from 0 to 1. So if I bring this back, actually I can plug this into the shininess. Sometimes it doesn't display properly, but when you bake it out and put it into a render view or try to render this as a material, it will actually display properly. At the moment, it's, for some reason, it's just not displaying properly inside of Rhino, but in the shaded view. But you'll see with this, if I actually bake these out, I can bake these, and what it will do is that although it won't display it properly in shaded view, when we go into our rendered view, you'll see that it is actually a shiny or not a shiny material here. And if we go into our materials library, so if you type in materials, you can see that it's actually created 2 custom materials, and they've when I baked out those two objects with these materials, it's automatically created these as materials inside the materials library. So if we go back to Grasshopper, what I'm going to show you now is a way of doing this without actually creating the materials themselves. What we're going to do is that we're going to color a mesh. We might start with this walkway support. And what I'm going to do is I can say mesh from sub D. And plug this in here. And it's just going to turn this into a mesh. And then there's a component that we can use called mesh color. So if we plug this mesh color component in, and we can specify a particular color if we want to. And so the color that we might take might just be like a lighter version of the previous swatch. And what you'll notice about this, if I press this green preview component, so I'm only previewing out what I'm selecting, and then I also undo the bake of those last materials, is that when we preview this component, we can see all of these mesh edges. So we can click on display and then preview mesh edges and turn that off. And when we bake this out, actually maybe for the purpose of this exercise, I'll make it a little bit more colorful. And what you'll find is that you'll actually be able to preview this out inside of shaded view, and if you go to rendered view, you'll also see this as a preview. But if we go to our materials library, you'll see that it doesn't bake it out as a material. And the reason that it's done this is because it's not actually a material that's applied to this geometry. It's an inherent part of the geometry itself. So meshes can actually have colors for each of the vertexes within the mesh itself. So if we were to delete this, swatch here, and then delete what we just baked out and bake it again, you'll see by default there's a whole range of different colors. And what this is going to do is for each of the vertices in this mesh, so each of the points that make up this mesh, it's going to give it a different color, and that's why it's looking all weird and random like this. This will start to make a little bit more sense when I show you the next part of this tutorial. But yeah, basically what you just need to understand is that it's an inherent part of the geometry that will be overridden if you apply a material, but it can be useful because mesh color is previewed out when you bake it inside the shaded viewport by default, and also in the rendered viewport unless you apply a material to it. I'm going to show you another way of doing this so that you can understand a little bit more about meshes themselves. So we're going to do this to our base geometry here, which by default is made up of two different surfaces or poly surfaces. So we can say mesh rep to turn it into a mesh. And I might also turn off this preview setting over here so that I can see everything that's currently previewed. And then we can go back to this. And I'm also going to turn back on our preview mesh edges so that we can see the edges of our mesh here. And what I'm going to do is I'm going to use a component called deconstruct. Construct mesh, which is this one here. And you'll see that when we deconstruct a mesh, what it will break it into is a bunch of vertices and faces and colors. Whereas when we say deconstruct rep, so deconstruct like a surface, and we plug this in here, what we'll get are the faces, edges, and vertices as well. The difference here is that when we use a panel to actually look at this information, the faces are built up of a list of different faces that can be baked out. But once we turn it into a mesh and we deconstruct that mesh, what this actually shows is a bunch of, let's say, like assembly procedures for how you would actually use the vertices to make up the different faces. So here we've got our vertices and here we've got our faces. So these are the points that make it up, and then the faces are like the assembly instructions for how to actually make each point up. The point is that if we were to bake this out, it's not actually going to bake any faces like it would if we baked out the deconstruct brep. It's only going to bake out the points. So there are no... Deconstruct mesh doesn't work in the same way as explode mesh does. So if we said mesh explode, what this will do is that it will break it into all of its individual faces. That's not how deconstruct mesh works. If we wanted to reassemble this together, we could use construct mesh. And what we would need to do is plug in the vertices, plug in the faces, and then you'll notice here that inherent within meshes, you can actually change the colors. So you can bake in colors. And what we're doing here is that it bakes in the color for each one of these vertices. So if I was to put in a swatch and I was to make this black, like so, then this mesh would be colored black. But we can still see the red mesh lines here. And this is the way that we can deconstruct and reconstruct meshes. What I'm going to show you is that we can actually create like a gradient of colors. So I'm going to turn the preview of all of these parts off. And I'll turn the preview of all of these parts off. And what we're going to do is we're going to take our central column that runs down the center of it. And I'm going to make it black up the top and then white down the bottom. And the way that I'm going to do this is I'll type in mesh from subd and plug it in here. And then I can deconstruct this mesh. Or if you type in demesh, it'll usually come up, deconstruct mesh here. And then what I can get is I can get these list of vertices. So these are all of the different points that make this, that make up this geometry. And I can actually deconstruct these points. So I want to teach you all the different ways that you can deconstruct things. So deconstruct points will break things into an X, Y, and Z coordinate. So see down the bottom here how we've got our X direction, which you can see because it's labeled X over here. And then you've got your Y direction with the grid because it's labeled Y here. And then Z is the height. So we want to find the heights of these. And when we plug in our panel, we can see that all of these different heights will be listed here. So from a negative height of 1.4 up to 124, and so on and so forth. And what I'm going to do is that I'm going to use this height data to actually color each of these vertices. And the way that I'm going to do it is with what's referred to as a gradient component. So if you type in gradient, and you get this gradient here, then we can actually create a set of gradient or a gradient of colors. To show you how this works before we sort of plug it in here, I'm just going to, what I might do is that I might set a few different points. So if we say point, and say set multiple points, so 1, 2, 3, 4, and then I might make some spheres. And I might make the radius 25. It's probably a decent scale for them. And then the next thing that we're going to do is we'll use a custom preview component to preview out these colors. And so this is going to be our geometry, and this is going to be our material. Now, the way that this works is that you need to assign a numerical value for each of these spheres. So to imagine this, what I'm going to do is that I'm going to say 0.1, let's say 0.4, 0.6, and then let's say 0.9. And then just so that you can see what's going on here, I'm going to plug all of these into a panel. And then I'm going to plug each of these into this parameters component. And then I'm going to explain to you exactly what's happening here. So this range of gradient colors, I want you to imagine as like a range from 0 over to 1. So we can imagine that 0 is here and 1 is here. Imagine then that 0.5 is here. And so what's happening here on this list is that anything that is labeled as 0.1, so in this case it's the first sphere over here, is going to be placed roughly around there, and that's what color this is going to get. This sphere over here, which is 0.6, is going to be placed sort of roughly over here, and so that's what color this gets. With this gradient tool, you can right click on it and you can change the presets of the colors. So we could make this multicolored like this. So you can see that 0.1, which is the first sphere, is roughly like here. 0.4 is roughly like here, which is the second sphere. 0.6 is roughly here, which is the third. And then 0.9 is here, which is the fourth sphere. The other thing that we could do, if I right click and I change the preset again, let's make it from like black to white, is that I can either right click on this color and I can change the color itself like this, or I can double click on this little circle and I can change the color from left to right. So I could like click here and I could choose a different color if I wanted. Like that. So this is the way that the gradient color works. And this is why we set an upper and a lower limit. Because at the moment, our lower limit is 0 and our upper limit is 1. So that's why we, on our range of numbers, imagine that 0 is here and 1 is here. If we were to set an upper limit of 10, then it would go from 0 through to 10 over here. So like 5 would sort of sit here. And that's how we control all of this numerically. And this is how we arrange all of this data. So if we take this back to our column that we're creating here, so we've got all of these different values for height, what we can see is that these numbers don't fit between 0 and 1. Like they go very, very high. And so one of the mathematical components in Grasshopper is called reparameterize. So reparameterize numbers. And what this will do is that if you plug in any numbers like this, and then I'm going to take this back over here, it will find what the smallest number is on that list and the largest number is on that list. And then it will remap all of the numbers that are within that list to be between a bounds of 0 and 1. So that now the smallest number on that list will be 0 and the largest number on that list will be 1. There are other ways of doing this, but for the purpose of this exercise, this is what we're going to go with. And so what I can do now is that I can use a gradient component. Like this. And I can plug in these as our parameters. And I'm going to change our preset to go from black to white. And then I can use a construct mesh component. And so I can plug the vertices into this vertices, the faces into this, and then I can use this to set the colors of each of these vertices here. And if I turn the preview off of all of this, and then I can also go to our display up the top, and we can turn off preview mesh edges. Actually, there must be one other thing that's previewing, so that's this. We can turn this off. And now you can see that these colors, as it goes across this gradient, go from white to black. So we could pull this over this way, so we can make it from black to white if we wanted to. Or we could change to a different preset to make it all colorful in that way. And so this is one of the varied ways of actually changing all of these different display settings. There's two more things that I would like to show you. And this is how we can preview out points and also how we can preview out curves without actually creating points and curves, because they can become quite computationally intense and make your computers really laggy. So what we can do if we have a bunch of points, and I'm just going to do this manually for the time being, and you can do it too, is just make all these points, and then we can type in cloud display, and we can set the color. So I might just choose a swatch and set that to red, and we can choose a size that we want to display this at, and it will create like a cloud of that particular color to display all of these points. And then similarly, if we had a curve like this, we can use a component called custom preview line weights. This one here. And what custom preview line weights does is that we can set our curve that we've just created into here. And then for our shader, we can just set a particular color, and then we can choose a thickness for the curve as well. And then it'll start to display out the curve like so. As well as all of these different display components, I thought it would also be helpful to show you how you can actually create animations inside of Grasshopper as well, and also how you can control the perspective and the camera of Rhino inside of Grasshopper itself. So to do this, what I'm going to do is take all of these different display components that we've inputted so far and just delete all of them. I'm also going to delete the curve that we made inside of Rhino itself, because we won't need this anymore. And I'm going to start by showing you how we can make animations. To do this, what I want you to do is make a number slider. Let's input the number 32, because this will make a number slider between 0 and 100. And what I'm going to do is make a sphere. By default, this sphere will be in the base position, or if you wanted to, you can right click here and say set one plane, and we can actually set the plane to be in a particular location if we want to. And then we can control the radius of this sphere, like this. And it will actually run through all of these different values, and it'll save a screenshot along each of them. So let's give this a try. Let's right click and we'll say animate, and you'll see that you'll have all of these settings that come up. So the first one is choosing a location. So I'm just going to set a random folder. The next thing that you can do is that you can choose the file name template. So here I've just called it frame, and then it's going to have whatever the frame number is. So in the animation, it will be frame 1, and then image 2, it'll be frame 2, then image 3 will be frame 3. Just remember from our Rhino tutorial in making fly-through animations that if you're making an animation video, usually you need roughly 30 frames per second. So if you're making a 10-second animation video, you would need 300 frames for this. And we can set this frame count down here. I'm only going to make this as an example, or if, for example, you wanted to make a diagram or something like that, then maybe you would only need a frame count of roughly 10. And you can also choose what viewport it is. At the moment, I've just got perspective, which is the active viewport at the moment. You can set your resolution to be whatever you want it to be as well. And when you press OK, it will run through 10 of the iterations within this number slider. So the number slider goes from 1 to 100. So it'll divide it up into 10 points along the values that it could be. So it'll probably be 10, 20, 30, 40, 50, 60, etc. So if we press OK, you'll see that it'll run through all of those values, and it's saved out an image at each of those values. So if I go to this folder, you can see all of these images have been saved out. So it's frame 000 and then 00001 and so on. And it goes from smaller to larger, like this. Now let's delete this. And what I want you to do is that I want you to actually select all of these components that we've got inside our bake group and just bake them out. And let's go to our monochrome viewport. and I'm going to show you how we can control the camera inside of Grasshopper as well. So something that we can do here is that we can use a component called Set Camera, this one here, which is a part of a plugin called Horseia. So if you hold Control and then Alt and click on it, you'll see that it'll bring up this plugin itself, and it's got a few different components inside it. And there's a few different options. So we've got camera location, we've got camera target, we've got lens length, we've got up direction, and we've got activate. So if we start setting a few of these, what we can do is we'll set a point for the camera location, a point for the camera target, and then a lens length. So a typical lens length would be like 24, so that's a standard lens length of most smartphone cameras. And then to activate it, we'll use a Boolean toggle, which will let us choose a true or a false value. So if we have false, then this isn't going to actually change our view. So our camera location, let's set one point, which can be maybe over here. And then if we select this as well, and we have our gumball turned on, we can move this point to wherever we want, so we could move it upwards. Then we can also set a target location, so let's set the target that we're aiming for to be inside our pavilion that we've created. Now, if we turn this on, you'll see that it'll actually change the camera location. And if you want to see an example of this working, you can change the lens length and it'll zoom in and out. You'll hopefully remember from the Rhino course that if we've got a very low lens length like this, it'll have almost like a fisheye lens. If you've got a very high lens length for your camera, then it'll create a really flat effect like this. So lens length affects the distortion of the image itself. There's something else that's really cool that I want to show you. And this is that we can create fly-through animations. And the way that we would do this is that we can draw a curve manually inside of Rhino. So if we have a curve that goes through like this, and then we might move it upwards, like this, what we can do is that we can set this curve into Grasshopper itself. So I can reference this curve in, say set one curve, then I can hide that curve. Maybe I'll turn but I'll leave the preview on. And then we can use the evaluate curve, or if you type in eval curve, then you can say evaluate curve. Make sure you choose evaluate curve rather than evaluate length. And if we want to, we can say, let's put an input of 0.12 so that we get a number slider between 0 and 1, but we get 2 decimal places. And when we plug this in as a parameter, it'll only go between 0 and 1 units. So that's like 0 and 1 millimeters here for me. But if we right click here and say reparameterize on this curve input, reparameterize this curve so that the inputs are between 0 and 1. So see here now it's in percentage terms. So from 0 up the start there to 1 will be towards the end of the curve itself. And what we can do here is that we can turn the preview of this off so that it's invisible. And we can set this to be the camera's location instead of having it be like a manual curve. And this way, it'll let us evaluate along that curve and we can create a fly-through animation like this. And so we can actually animate this number slider by right-clicking on it and saying animate, and I'm going to set a different folder, which will be called animation fly-through. And maybe I set 50 frames this time instead of 100, instead of 10. And when I go to press OK, it will render out each of these frames, and I can make a video animation from it if I wanted to. I'm not going to show you how to turn these frames into an animation movie file, but if you want to, you can reference back into the original Rhino course where I show you how to do that. And the great thing about this is that because it saves out whatever your Rhino view is, we can use all of those display settings that I taught you earlier to use custom previews or colors or materials, or even things that are baked out into the Rhino viewport like I'm showing you here, and it'll create screenshots at each of these different points.
Amazing work getting through this modeling exercise. The next topic that I'm going to take you through is something that's referred to as data structures. This is without a doubt the most important topic inside of Grasshopper, but it's a topic that I would say 99% of people that use Grasshopper don't understand properly, and it's the number one thing that holds people back from having an advanced understanding of this program and feeling really comfortable inside of it. This is because people tend to find it very technical and usually quite overwhelming, but if you pay attention for the next 40 minutes, I will endeavor to demonstrate these concepts in the simplest, most effective way possible. So please do not give up. This is the number one thing that you can actually spend your time in to create the most holistic understanding of this program. Again, it's only 40 minutes, so just spend the 40 minutes going through this until you feel really comfortable with this as a topic. You will thank yourself for it in the future, I promise you.
Okay, so amazing job getting through all of that stuff so far, guys. You've now got hopefully a really good general understanding of how we script inside of Grasshopper and how we connect components together and how we can adjust things parametrically. But there's one more thing that I want to introduce you to, and this is referred to as data structure and list manipulation. So let me show you what I mean by this. Let's start off with some basic list structure, and I'm going to annotate this as we've done before. So we'll say scribble. We can make it a bit bigger, and we're going to call this first exercise one basic list structure and manipulation. And what I'm going to do is that I'm going to start with one referenced point. And I might just set this to be in the center of our model here. And I'll double click on this viewport to enlarge it so that we can see it. And what I'm going to do is that I'm going to move this point that I've set. And again, we need a direction. So I'm going to move it in the X direction across here. So we can say unit X. Like so. And then I'm going to create a series component again. Remembering that series is one of those counting components, so at the moment it's going to count up to 10, but we could set it to count to whatever we wanted to, so I could set it to count to 8, for example. And you'll see that now it's going to create 8 movements, because it's moving at all of these 8 values, so 0, 1, 2, 3, 4, 5, 6, 7. And the next thing that I'm going to do is that I'm going to create circles at each of these points. So we can use this circle component over here. And these are a little bit large for the time being, so maybe I'll set it at something like 0.3. And we can select this circle component and say zoom, and zoom in like this. Now, in order to show you how lists align, what I'm going to do is that I'm going to create a parametric relationship between how far each of these points are moved across and the size of these circles, which is really easy to do. All that I'm going to do is link this information here with the circle radius. So to preview this, we can use a panel, and I'll plug this into the series component and maybe drag this across to make it a bit bigger so you can see. And so you can see that this series component now has a whole bunch of different values from 0 down through to 8. And I can actually replace this into the unit X input here. So all of these numbers are affecting how far it moves in that direction, but we also wanted to affect the radius. You can see that these numbers are all a lot larger than what our value of 0.3 is, so maybe I might divide, or say division, and I can divide all of these numbers by 10. And then I can drag this down and hold Alt, or press Alt, and then plug this into the radius. So you can see exactly what the radius of each of these circles are going to be. Now, there's a few things that I want to introduce to you here. Firstly, is that there's a bit of terminology. So if we look at these lists, you'll see that there is a lot of information that's shown here, or actually let's go down to this list here. So this is the radius of your circles. So the first piece of information is, let's say, 0, 1, 2, 3, 4, 5, 6, 7. This is what's referred to as the items on your list. So it's item 0 corresponds with 0, item 1 corresponds with 0.1, item 2 corresponds with 0.2. So that's the item number on your list. This is the actual data itself. So 0, 1, 2, 3, 4, 0.4. And this represents what the radius of each of our circles is going to be. And the final thing is that there is this number up the top here. So this is what is referred to as a branch. And what we can see here is that the items on this list are corresponding perfectly with the items on this list. So see how the branch name is exactly the same. So it's 0, 0. And then there is 7, or it goes from item 0 through to item 7, and same with this, so item 0 through to item 7. And what's basically happening here, if we drag this down to here and this down to here, item 0 on this list is corresponding with item 0 here, 1 is corresponding with 0.1. So we can see this here that when it's moved 0, the radius is 0, when it's moved 0.1, or when it's moved 1, the radius is 0.1, when it's moved 2, the radius is 0.2, so moving 2, radius is 0.2, all the way up to 7, where the radius for 7 is 0.7. Now there's another thing that I want to introduce you to, and this is when we get nullified data or corrupted data. So if I was to say divide curve here, what divide curve does is that it will divide it up a certain number of times. In this case, by default, it's dividing it up 10 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this is turning red at the moment because one of these curves, which is here, has a radius of 0. So you can't divide up a circle that doesn't really have a radius to it. When we look at this data across here, you can now see what's happening here. So each of these branches represent, so the branches being these darker grayer parts, this represents the data for each of these circles here. So you can see on that first circle that there is actually no points that it's divided up. And so we have to go to the next branch, and then we get all of these points here, and then the following branch, you get all of these points down here. And what this has done is that this has automatically done something referred to as grafting, which I'll explain to you in more detail in a second. And the way that this works is that for each of these circles, they've given that circle its own branch here. So the circle that was item 1 on this list now gets branch 1. I know that this is probably feels quite complicated and quite boring, but it's incredibly important to be really, really good at using this particular program if you want to. And so it's automatically grafted all of this, and then the data inside of each of these represents each of the points that it's divided up. So we can see here that if we divide it 5 times instead of 10 times, so that there's only going to be 5 items on each of these lists. So you can see that these lists get shorter over time. And then the other thing is that if we specified fewer circles like this, like if we only had 2 circles, you can see that there would only be 2 branches here. But I'm going to undo this. So we'll say 8 circles, and maybe we'll say 5 points on each. And so when we go to the top of this list, you'll see that there is an entire branch that's empty. Sometimes instead of that branch being empty, it will actually say it'll actually still have the items on that list. Actually, we can see whether that works here. It'll actually have the items on that list, and they'll say null, or it will say corrupt or something like that. And so what we can actually do with this data, if we need to clean it, so if we want to remove those branches that have nothing on it, and if we want to remove any data that's corrupted, we can say clean tree, and we can plug our tree into this. And it gives us a few options, so we could remove any corrupted data, we can remove any invalid data, so if you've got like broken meshes, it'll remove that, and then this removes empty branches if you want to. So if we plug, or I might make this a bit smaller, and if we plug this into here, you can see that it hasn't removed that branch, so I can use what's referred to as a Boolean toggle. So Boolean toggle here. And I can say true, and then it'll remove any empty branches and any mismatched data. Now, the next thing to note is that when we use that list item component, so say list item, like this, and it asks us for an index, so I might say 2. So this will give us the item number 2 on that list. If we were to say item 3, it'll go to the next item like this. And that's because this list looks like this. So it goes from 0, 1, 2, 3. So when we say 3, it's taking this third item off the list, which is the circle with radius of 0.3. But when we plug this in over here, so when we plug this over here, and we say we want the third item on each of these lists, what this is actually going to do is it'll give us a point on every single one of these circles. And the reason that it's giving us a point on every single one of these circles is because it's taking item 3 from every single one of these lists. So item 3 on this list, item 3 on this list, item 3 on this list, and so forth. So it's going to do it for all of these different ones. So if we wanted to get the data from all of these different circles on this particular, or on a particular circle, there is a way to do it. What I'm going to do is that I'm going to firstly use a component called simplify. And so see all of this data that runs along here and how each of these branches has a particular notation. So it's 0, 0, 5. All of these zeros don't actually matter. They sort of add spacing every time you run one of these components. It'll add a 0 to it, but it hasn't actually, the data doesn't really matter. So we can use a component called simplify tree, like this. And simplified tree will actually get rid of any of these branch numbers that don't matter. So see now it just says branch 1, branch 2, branch 3. This can make things a lot simpler. If I get rid of this component here, so simplify tree, there's another way of doing this, which is to right click on the output here, and you've got all of these data options here. So you could flatten, graft, which we'll go through in a second, or you can simplify it. So you can simplify that data without having a component in itself. Now, the next thing that I'm going to do is that I am going to change the values of this divide curve, and I'm only going to have 2, or I'll have 3 divisions on each of these, but I'm going to change the number of circles down to, let's change it to 5, like so. And so see now we've got 1, 2, 3, 4, and these represent the circles. So this is circle 1, circle 2, circle 3, circle 4. And then this is point, these are the points. So how we've got 1, 2, 3 points. So we've got 0, 1, 2. So 3 items represent those 3 points there. If we wanted, we can flip this entire thing around. And what I mean by that is, let's just type in flip matrix. Again, this is a really complicated thing to do, and you're very rarely going to need to actually do this, but please watch on and understand, because it can be really, really important to have a great understanding of data structure. And see what's happening here is that what it's actually done is that it's taken item 0 on this list, and item 0 on this, and item 0 on this, and item 0 on this, and it's actually turned this into, or item 0 on this list has gone here, item 0 on this has gone here. And so what this has actually done is that it's taken each of these branches, and see how there's 0, 1, 2, 3, 4 branches? It's now replaced the branches with the items. So now there's 0, 1, 2, 3, 4 items on this list. And see how previously there was 0, 1, 2, 3, 0, 1, 2, 3, and these were the items on the list. Now there's 0, 1, 2, 0, 1, 2, which, so the items have become branches and the branches have become items. And to visualize what this means, because this probably feels extremely unimportant and a little bit confusing, but I'm going to really go into detail in this, and I promise you by the end you'll start to understand a little bit better, or once you watch this around the second time you'll understand it a little bit better. See how under list item, so this is choosing item, let's start with item 1 or 2 or 3, and it's changing those items around, whereas once we've flipped this matrix and we've flipped that data around, now when we go from item 0 to 3, see how it's choosing each of those circles individually? And so it's flipped all of that data around using that flip matrix. We're going to go through more exercises about this in a second, but this is just really important for things like if we're creating notes or like fabrication notes. So panel 3 goes to panel 4. It's really important to be able to control data like that. And it's also really important to control where that data is actually placed. So where on your panel that's placed. So we're going to move on to the next exercise. I'm just going to group all of this together, and maybe I will change the color of this as well. So I'll make it like a light blue. And then I'll copy and paste this down. And the second thing that we're going to go through is called grafting and flattening overview. And this will start to make a little bit more sense. I'm also going to take all of this stuff and I'm just going to turn the preview off on it because we're going to effectively start again. Okay, so for this exercise, we need to set a point as well. So let's do that. We'll say right click, set one point, and we'll set it back in the center again. And we're going to go back up here and we can copy this script out. So we just need the move, where we're moving it, and the series for the time being. And I might just copy this down because it'll be a little bit faster. And we can get rid of this panel as well. And I can turn the preview on here. And so what you can see is that we're moving it across a certain number of, we're moving it across a certain number of times. But I also want to control how far we're moving it and where we start. So I'm going to set it at that at 15. So it'll mean that this is spacing of 15 like this. So larger spacing than what we had last time. See how this will change the spacing? Now, I also want to represent this in a particular way. So what I'm going to do for this is I'm going to use something called a cloud display, which is this component here. So we can plug that point into here. And I'm going to set the color with a swatch. So color swatch, and we'll set it to be yellow. But we can't see this at the moment, so I'm going to right click here and I'm going to change the size to 10. Just so it's a little bit larger. And now I also might group this together and I'll change the color just so it's easier for us to actually follow along with this. So you know that this part of the script is the yellow part. And now same for this move component. I'm going to copy this cloud display across like that and plug this in over here. And maybe I might make this one red instead. Like this, and then I can group that together and I can change this color to being red too. Now, the next thing that I'm going to do is that I'm actually going to move this in a different direction. So what I'm going to do is I'm going to, instead of moving it in the X direction down here, I'm going to move it in the Y direction like this. So we can copy this, or we can type in move, and then this is the geometry that we're going to move. And instead of moving it in the X direction like we did last time, we'll say unit Y, like so. And then we're going to move it in the same amount as what we did last time. So see how it's moving each of these upwards like this? And then I can copy this cloud display and maybe I will make this green. And then I can group all of this together and we'll make this green so that it's easier to follow. Okay, so now we've got the way that this script is working, which is we're starting with a point that's referenced here. And this is yellow. Over here. And then we're moving this we're moving this point across this number of times. So we're moving it across 7 times, and we're moving it 15 units each time, so 15 mil each time. And then over here, we're also moving it upwards as well. So we're moving it up the same number of times. And what I'm going to show you is with this panel here, we can plug how you're moving it over here. And same with over here, how we're moving it like this. And so the really important concept here is that all of this data lines up. So we can take circle 0, for example. So circle 0 is actually this one. It's item 0 on this list. And what's happening to circle 0 is that we are matching this up, where 0 is now going to be moved upwards by 15 mil. So see how it goes across by 15 mil and up by 15 mil. And so this is why it ends up here. And so same with this one, the one that's moved across by 30 mil is then correspondingly moved up by another 30 mil. And you might be saying to yourself, well, yeah, this is pretty basic. But what I'm going to show you next is a component called grafting. So there's 2 ways to graft data. We can either type in graft tree, and we could plug this in like this, and then plug it into motion. But there's a shortcut as well. So instead of that, what I'm going to do is right click here, and I'm going to say graft like this. And now what you can see is that there's 2 big changes that have gone down. Firstly, each piece of data on that list, so each item now receives its own branch. So see how each of these are now item 0 on its own branch. And the second thing that's happened, and I'll zoom out just to allow you to see, is that when we right click here and say graft or ungraft, it's going to change the number of circles that are actually developed out of this. So see how now what's happening is that each time we try to what's referred to as align or lace or match this data, item 0 on this list is aligning with item 0 on this list here. But then it asks for, say, for example, item 1 here, it'll say, where do I go and what do I align to? So if we look at circle 1 here, and what's actually going to happen is that previously, before we grafted it, if I use the snipping tool to make an annotation, you can see that item 0 aligned with item 0 like this. Item 1 aligned with item 1, item 2 aligned with 2, 3 aligned with 3, 4 with 4, 5 with 5, etc. Whereas, when we graph this data like this, what's happening here is that item 0 aligns with 0, and then 1 is saying, well, where do I align to? And so what ends up happening is that it aligns every single way, like this. So all of this aligns together. And then for item 0 on this list, what ends up with this is that this will also align with all of these individually. And then the same thing will happen down here. So this will align to here and so forth. So this will align to every single one of them. And then this will align to every single one of them as well. Like so. And this is what grafting does. And so what ends up happening is that before we graph this, you can see that for these red ones that run along here, there are currently 7 items in this list. And say, for example, here, there are also 7 items in this list at the end. So there are 7 green items that run across like this. But as soon as you graft the input to here, so this is now grafted, but this is not. So this data aligns like that. That you're going to get an exponential number of items resulting from this. So see how we've now got 49 items because it's 7 times 7. So for each of these points, so we're taking 1, 2, 3, 4, 5, 6, 7 points, and we're moving each of those points up 7 times. And so that's why we're getting 49 outputs rather than 7. And so this is just something that you need to be really conscious of, because if you're doing something with heaps of panels, like 1,000 panels. So it'll end up being 1,000 times 1,000, which will end up being over 1 million results instead of 1,000, which is an enormous amount of data for your computer to compute. And so the number one reason that Grasshopper crashes is because some items will be grafted and some items will not, and the data won't be aligned. And so the next thing to show you is that another thing that we can do is something called flattening data. And so this is the opposite of grafting. So you can right click here, and instead of graft, you can say flatten. And what this does is that it takes all of your data and it will actually put it onto one list. So see how this is now all on one, only has one branch. So if we graph this again, and we can actually visualize the data that comes out of this, and you'll see that there are now 7 branches with 7 items on each. So see how there's this branch and then this branch, but if we flatten all of this data, it'll get rid of all of that data structure and everything will be on the one list under one branch, and there's just 49 different items. So it goes from 0 to 48. So this is what's referred to as grafting and flattening. Again, we're going to go into more detail about this in a second, and going through basic list structures and manipulations. And this will still continue to reinforce your understanding of all of this, and it'll make you extremely strong in using this program. But you need to spend the time actually going through these exercises, and you may want to actually rewatch this video after you've gone through it once, because this is the one thing about Grasshopper that everyone finds very overwhelming. But if you spend an hour or two actually investing in learning it, you can become very, very strong at using this program. Okay, so what I'm going to do now is I'm going to select all of this and turn the preview off. And we're going to go through some more basic list structure and manipulations. You'll see, though, that once we've actually turned off these cloud displays, they're still visible. For some weird reason, custom displays typically... Okay, and so what we're going to do next is we'll take this and we'll copy this down, because this is going to be exercise 3. And what we'll say for 3 is basic list structure and manipulation. And so what I want you to do now is that the first thing is that we're going to reference in a plane. And the plane that I'm going to reference in is, if you type in XY, it will actually make a plane out of the X and then the Y axis, like this. So it's just a basic plane in the center of your model. You can change the size that a plane is actually displayed at by going display and then preview plane size. And maybe we might set this to 5 instead of 500, and see how now your planes will become much, much smaller. And what we're going to do with this is that we're going to make a square grid. So you can type in square like this, and this will make a 2D grid with square cells. So this is the plane that we're going to use. We could also use a point if you wanted to. And then it asks us for the extent in one direction. So we'll say we want it to be 5 across in the X and then 10 across in the Y. And so if we turn the preview off of this plane, you can see here that this is our little grid structure, or our cells. So see how this can make more or less cells. So it's now a 5 by 10, but we can change the size of these cells, and I'm going to set these to be 10 mil each as well. So it's a bit bigger. So see, this affects the size, this affects the number in the X direction, and then this affects the number in the Y direction. Now, the next thing that I want you to have a look at is that I'm going to type in point, because this will actually show you all of your individual points at the edges of these cells. So see, these are all of the different points. You'll notice that this wire looks different to this wire. This is something you may have noticed earlier as well. So whenever there is grafted information, or if there is branches in a tree rather than a list being flat, your wires are going to be displayed as dotted rather than as straight like this. And so the next thing that I want you to do is that I want you to type in something called parameter viewer. So param viewer, which is this one here. And what this will actually let you do is that it lets you see the information inside a particular list. And so you can see here that there is data with 6 branches, and these 6 branches here represent the 6 cells across in this direction. And then there are 10 items in each list. So see how it goes from 0 through to 10. We can also simplify this, which will get rid of all of these zeros. So you've got 7 branches with 6. So 7 branches, so 0, 1, 2, 3, 4, 5, 6. They're your 7 branches, and each one of these has 11 items in them. So you can see here that you can change this around. So now it's got 9, 8, 7, 6, or you can have more branches like this. And so this is the importance of actually having this sort of data structure. And I'm going to show you why in a second. But first, what I'm going to do is I'm going to label each of these cell positions. And the way that I'm going to do this is that I can use a text component. I'm going to use this one here, which is quite bold. So it says text for laser cutting or milling. So you can set a location, text, and a size. And the text that we're going to set is that what I'm going to do here is I'll create a list length component, and this will tell me how many items are in each of these lists. So if we actually look at this with a panel, see how it says that there's 11 items in each of these lists like this. So it goes from 0 through to 10. So there's 11 items on each of these branches. And so what I can do with this is that I can say series, and I can have each of these count up to 11, and I can plug this into my text, and then I can plug this into the location, and I can change that text size. So I might make it a bit bigger. I'll say 5. You'll see what this will do in a second, but just write out this script for the time being. And then I'm also going to turn maybe this preview off for each of these. Okay, so what we've now got is a script that creates a square and then labels each of these items on the list. So I'm going to say label each item on the list, like so. And so what you can see here, if we say list item, and we'll say item number 2, if we plug in this list, see how now this is selecting item number 2 on each of these lists. If we change this around to item number 3, it's going to select item number 3 on these lists. And the way that this looks like is that we're taking each of these. So we've got, as I was saying earlier, 6 branches. So 1, 2, 3, 4, 5, 6. And then it's taking the third item on this branch, third item on this branch. So each of these 6 branches represents our 6 cells in the X direction. So 1, 2, 3, 4, 5, 6. They represent our branches. And then this data across here represents the items in each list. So this is item 3 or 4 or 5 or 6. So another way of visualizing what we did earlier, if I delete this, is that we could use that component called flip matrix. And we can plug this in over here and then plug this into here, and see how now instead of going 0 through to 11, it's now going in the other direction. And so it's like flipped this data around. And so this is what flip matrix does. If we bypass it, you can see that it looks like that. And so this is what we are doing with this particular information. Now, the next thing that I want to do is that I want to show you another component called replace items on list. But before I do that, actually, maybe I might introduce you as well to Cull index. So remember when I told you that there's list item and cull index. So cull index, if we plug this in instead of list item, we'll actually get rid of everything except for item number 4. So see, now you can see that item number 4 is left over, but it's, item 4 is deleted, but everything else is left over. So this is the opposite of list item. There's a few other things to note as well. So we could say cull pattern, and cull pattern will let you plug this in, and then you can set multiple booleans, for example. So this one says false, false, true, true. So it's false, false, true, true, false, false, true, true. And this is just how it deletes things. So you can give items a true or false value and it'll actually delete it around. The other thing that we could do is that we can say replace item. So if we say replace items on this list in particular, so you can plug our list into here. And then maybe we might want to replace item number 3. So that's the indices. So we want to replace item number 3, and we could make a panel. And maybe we mark that with like X. And so now it'll replace item number 3. Actually, we want to replace this series component. This is our list, sorry. And then we'll place that into text. And now you can see that it's replaced item number 3 with X. So you can replace items on lists as well. And just having a good understanding of this will really, really help you to develop up the ways that you can actually manipulate data inside of Grasshopper. The other thing that I can teach you is that if we delete this, and we plug this back into our text over here, we can do something called partition list. So instead of having 10 items in these lists, if we type in partition list like this, we could choose the size that we want to partition it into. So maybe we want it into 2s. And then so for every second item on that list, it's going to make a new branch. So see now how it's like, or we could set this to 4. So it goes 0, 1, 2, 3, and then it starts that list up again. So it's basically every time you reach 3, it creates a new branch to this. This is probably like quite a complex concept for you to take in at the moment. But as you start to try to solve problems, it's important that you understand that these components exist. Again, if we hold Control and Shift together, we can actually replace all of those wires, and I'm going to delete partition list. And I'm going to show you one more exercise after this as well. What we're going to do is that I'm going to take you through all of these different manipulations that we've made over again. So we can copy this down. So paste this. And we're going to call this for branch and path notation. And I'm going to show you a few tips and tricks and reiterate some of the concepts we've been through. I'm just going to move this downwards over to here. I'll put a relay here. And maybe I'll move it down like this. And what I'm going to do is I'm going to take you through what the branch structure looks like for each of these manipulations that we've done. So simplify, flatten, graft, flip matrix, etc., etc. And explain it a little bit more like visually. So firstly, let's bring up a panel, and we can plug this into our points output over here and drag this across. And then the other thing I'm going to do is I'll bring out a parameter viewer, which is this thing here. And so this actually tells us information about our data trees. I'm going to make one up here, and then I'll copy it down to here as well. And what I'm actually able to do is that I can double click this top one, and it's going to display what this looks like visually. So at the moment, what we've got is we've got 6 branches. So this represents 0 through to 5. So 0, 1, 2, 3, 4, 5. So that's 6 branches. Just think of this plus 1. And each of these have 10 items in it. So think of 10 plus 1, sorry, so 11 items in each. So the first thing I'm going to show you is simplify. Simplify tree. And what simplify does is if we drag this over, you'll see that it'll actually collapse the data structure over here like that, and it'll get rid of all of these zeros that don't matter. So because that, and it'll just leave behind the data that actually does matter. So it's a lot easier for us to sort of understand and compute. So see how it gets rid of all of these branches that don't matter, all of these, and it becomes a much simpler data structure. So that's simplify tree. The next thing will be, let's say flatten tree, like this. So if we plug this in, it'll get rid of all of these branches and it'll put all of this data, instead of being on 6 branches, onto one single branch, like so. So see all of this, all onto one branch. Now the next thing that we can do here is I'm going to show you what partition tree or partition list looks like. So if we say partition list, we can plug this in here, and we might say that we want 11 items on each list. And what this is going to do is it'll break all of this data up. So you can see that now there's 11 items on each of these branches, and it creates however many branches that it needs to divide it up into groups of 11, like so. Again, see how there's that extra 0 that doesn't matter? So all of these are zeros. So this entire, I suppose, like branch structure can be removed by right-clicking and saying simplify. Again, we can right-click here and say graft, flatten, simplify, reverse, whatever that may be. And then the last thing that I'm going to introduce you to, or second last thing, is graft tree. And when we graft this tree, what that's going to do is it'll give every single item its own branch, like so. So see how every single item now has its own branch? But the great thing about this is that we keep all of that original data structure. So see how it goes 0, 1, 2, 3, 4, 5. Actually, we can simplify all of this too. So when we go down, see how now this is branch, so it's 1, 8. So there's 2 pieces of data in each of these aspects. So we've got our initial breakup into 6 different groups. So 1, 2, 3, 4, 5, 6. So it's 1, 2, 3, 4, 5, 6. And then we have all of our individual items that branch off from that. And so what we can actually do here is that if we wanted to just get rid of one of these trees, or one of these pieces of info, we can say trim tree. And what trim tree will do is you can set a depth and it'll only cut off part of this as opposed to actually flattening it. So see how if I plug this into here, how it still keeps all of this data structure, so it doesn't flatten it and put it all into one list. And what this means is that when we group this, so if you if we click here and say group, and we plug all of this in, this will actually group anything that's in a branch together. So it'll group together these 10 items. And when we bake this, we can actually select this and see how now all of that data is grouped together, and all of this data will be grouped together in the same way as we can group things inside of Rhino itself. And so this is a really excellent way of actually manipulating that data in a way that isn't either just grafting or flattening it. And this is what it visually looks like in terms of all of these data trees. Again, this is a really complicated topic, but you're doing a really, really great job in terms of understanding it. You probably don't understand how you can actually use this at the moment to solve any issues, but it's really important that as you go forward and you start scripting and you start trying to solve issues, that you understand how to manipulate data like this. It'll start to make sense when you need to problem solve inside of Grasshopper, and it's really important you understand, even if you don't understand how the components quite work exactly, just understanding that they exist and that this is something that you can turn to as you actually problem solve, and that it's something that you've been introduced to. And maybe that means that you might just know that it exists, and then if you think that it's relevant to something in the future, you can watch another tutorial, but at least you know that it's there. Okay, the next exercise that we're going to go through is that I'm going to show you the machine learning applications inside of Grasshopper. Grasshopper's got an inbuilt machine learning genetic solver, which is referred to as Galapagos, but there are also different plugin alternatives called Wolsey and also Opossum, which are excellent, and I highly suggest for you to check them out. This is quite an advanced application of Grasshopper, which actually allows you to assess your designs and then change different inputs for them, and it will test each of these different inputs and it will give you the best possible result for the design itself using machine learning. So to get started with this, I want you to follow through by creating a new document, and we'll start by just saving this document. This way, if Grasshopper crashes, you'll always have that autosave file. And what I'm going to do is I'm going to create a script that creates let's call it like an outdoor garden area, and then creates a pathway between 2 points. And I'm going to try to optimize it to be the longest pathway possible. So to initiate this, let's create a plane surface. I'm going to make it 10,000 by 10,000 across. So this is 10,000 millimeters, meaning it's a 10 meter by 10 meter, let's call it a 10 meter by 10 meter garden area like this. And then what I want to do is that I'm going to generate a whole bunch of random points across this, and I'm going to have the pathway go through these different points from one side onto the other. And what I'm going to try to optimize through machine learning is making the pathway as long as it can possibly be by adjusting where these points are. So there are only 2 components that you really need to know about inside of Galapagos. One is the solver itself. This is called Galapagos here. And then the inputs, which are referred to as the gene pool. So let's put in a gene pool over here. And this sort of acts like a slider where you can actually change these results from side to side. If you double click on this, you can change the number of genes here. So at the moment it's 10, but let's set this to be 3 instead. And you can set a maximum and minimum value for these in the same ways you can set a maximum and minimum value for a slider. So I'm going to set the maximum as 1. And now you can see that you can change these between 0 and 1. And the way that Galapagos is going to work is that it's going to randomly change all of these different values and test what the results are, and then it's going to find the combination of values that produce the best possible result. So in order to actually input this into being randomized points, we can use the construct point component here. And I'm just going to take these numbers and I'm going to multiply them by this 10,000 value. And we can plug this into the x coordinate over here. And then I'm going to duplicate this down. So we've got a second one, and we can set this to be the y coordinate. And now what we're able to do with this gene pool is we can right click and we can say randomize, and it'll actually randomize all of these different values in the same way as this is what Galapagos is going to do later. Now the next thing that I want to do is I want to create a pathway between these 2 edges. So what I'm going to do is I'll use deconstruct brep in here, and this will give us the faces, edges, and vertices. So I want to take the particular vertices here. So we can take this first vertice, which is over here, and then I want to get the one which is over here as well. So if we go to list item, we can see that this now gives us the second vertice. And if we hit this plus icon again, it'll give us the third vertice over here. So I want to take it from here and then create a curve that goes through here and then here and then here and then over to here. And to do this, what I'm going to do is use a component called merge, and it lets us merge data together. So we're going to start with the first point over here, which is this one over here. And then the second one will be this over here, because these are all of the other points. And then the last one is that third point over here. And to visualize this, what I'm going to do is say interpolate. and plug in my interpolated curve. Now you see that it looks all funky at the moment. What I want is, I'm just going to flatten all of these lists out. And I'm also going to turn the preview for everything off except for this original plane surface, just so it looks a little bit better. Now we can randomize these values a couple of times and you can see that you're going to get different outputs. This one output in particular is going outside the bounds of our square. So what I might do is that I might move these over and I'll take our plane surface and I'll find the center point using an area component. And then we can take all of these points here and I might scale them downwards. So I can scale these geometries from this center point. And I might scale it down by a factor of 0.5. Like this. And what this is going to do is that it's going to take these points which are quite far off and it's going to move them inwards like this. So I can replace this input here. And I might just clean this script up a little bit. And see how now it goes closer within the actual plane itself instead of going outside the bounds of it. And then we can turn the preview for all of this stuff off. Now you know that I like to always make sure that I've got lovely clean scripts. And so I'm going to group all of this together and then I'm also going to label it. And this first part I'm going to label pathway direction. And I might make it a little bit larger too. And then lastly, I'll just change the color. Now these are all of our different inputs. The great thing about having a parametric relationship between the points and also the plane size is that it's always going to create the same pattern no matter what. So you always want to be creating the most robust scripts that you can right from the get-go. And then I'm going to label this as Galapagos input. Now the next thing that I'm going to do is that I'd like to make this look a little bit more realistic, so I can offset this curve like so. And I might offset it by 600. So 600 mil or 0.6 of a meter. Now there are two ways that we can turn this into a solid. The first way is that we can loft in between. If I double click here and create a node, we can loft between the original curve and then this new curve. Just make sure that you flatten the values. But you'll see that this doesn't work particularly well if we had slightly different inputs like this. See how it's actually self-intersecting itself as a loft over here. And so what I want to do instead is I'll delete this loft input and I'm going to take the endpoints and I'm going to use planar surface, but to do this I need to close this curve up. And so what I can do is I can take the endpoints of each of these curves, so the original curve here, and then the offset curve, and see how now I've got these endpoints, and I can create a line in between the start and the start of this curve. So it creates that line there, and then the start of this curve, and then the start of this curve like that. And I can join all of these curves together. So I can join the original curve like this with the offset curve with the curves from each of the ends as well. And I'll just make sure to flatten this list off because if I don't flatten it, it'll be on different data structures and it won't join them all together as one curve. Now, I can use boundary surface, and you can see that it doesn't get that self-intersection, but it is intersecting the plane surface and it's making it hard to see. So I can say extrude, and I'm going to extrude it in the Z direction, so unit Z. Remembering that unit Z is the upwards direction. And I might extrude it by 30 millimeters. Now I'd also like to label all of this stuff out so that it's easy for me to come back and understand what's going on. And so what I can do here is I can group all of this together and we'll call this make pathway offset. And then we can call this extrude to be 3-dimensional. And then this is going to be labeled as an input for input path thick wideness. And then I can group all of this together and I can call this make pathway walkable. And I might also like to turn the preview of all of this stuff off. Now the next thing that I'm going to do is I might use my custom preview settings to change the colors of each of these elements. So I can say custom preview, and I might start off with our extruded pathway, and I can set a swatch color to make this dark gray. And then I can also take our original plane, so it's this plane surface over here, and I might like to use some nodes so that it's a little bit cleaner. So it follows like a roughly the same pathway, and I can make this a different color. So I might make this a light green, so the same color as grass. Like that. And now we can see that there's a concrete pathway through our grass garden area. Now, in order to start optimizing this inside of Galapagos, what we're going to do is we're going to take our Galapagos solver component over here, and let's place it over the far right hand side of our script. You'll see that Galapagos requires two inputs, so it requires a genome and it requires a fitness. Now the genome is what we can alter to change the outputs. So I'm going to plug these two gene pools in because these are the numbers that we can randomize, like so, and it's going to change all of these values again and again and again until it reaches the best possible value. And then the other thing that it requires is this fitness value. So this fitness value is the way that it actually tests whether an output is good or not. And what this is that we feed in a number like this, and it's actually going to try to make this number either larger or smaller. So you can see that there's these two wires, or the three wires that are connected. So connecting the two gene pools and then connecting this fitness. So in this case, what I want to do is that I'm going to take our original curves over here, or if I use our display settings up here and I click the green one, it's going to give us the curve of the surrounding the pathway. And I can do some analysis on this. So the analysis I'm going to do is test the length. So this component measures the length of a curve. And then maybe just to visualize this, I might plug in a panel into here. And you can see that this curve is 38 meters across. And so when I plug this in like this, and then I turn back off these preview settings, we've got our full working script. So I'm just going to save this, make sure that you save too. Now what we can do is that we can double click on our Galapagos solver and it'll bring up this menu. I'll explain a whole lot of this a little bit later on. It becomes quite technical, but for now, all you need to understand is that you've got this fitness value. We can either minimize this or maximize this. So it's going to change around the gene pool. So it's going to change around the positions of where our pathway goes through to either maximize the fitness value that we set. So it's going to either try to maximize this length or it's going to try to minimize this length. Now the second step is that we just need to go over to our solvers, and over here is where we can start solving. So if I click Start Solver, what you'll see is that it starts running through different results. Our display settings for this are over here. So by default, it's going to only display results if they're better. So if we get like longer pathways, it's only going to display the longest result. So it's only going to display the best result. Whereas if we click this icon over here, it'll display all of those different results all as it's testing through it. So you can see it's testing one after the next after the next. Now the next thing that's come through is that it brings up a whole bunch of the different results analytics that it's showing over here. So these on the right hand side are actually all of the different results that it's run through. What I want you to notice is that currently what's happening is that it's actually making the pathway go around like this, and it's found that if it makes the pathway spiral, it will create this like large area in the center, which is technically, according to the fitness value, so according to the length, the best possible outcome, but it's not actually the ideal outcome that we want. So this is almost like a technicality that it's found, like a fault in the system, because ideally you wouldn't want a pathway to actually do this. We'd want our pathway to just sort of like wind its way through and be quite elegant. And I've set this up because I want to point out to you that you need to be extremely careful in Galapagos about what you try to incentivize. So it's similar to when you're trying to, I suppose, like define ideal outcomes for AI. The example that gets used a lot is that if you created an AI that had the purpose of getting rid of spam emails, what you would expect it to do is just be really effective at culling or discerning between genuine emails and spam emails and then deleting the spam emails. But what it might find is that that's a really difficult task, and it might be actually easier to like hack into the Pentagon and find the nuclear launch codes and launch and kill all humans, because humans create spam emails. So maybe the most ideal way for it to accomplish its goal is to destroy all of mankind. That's not what you want. In the same way as when we're training all of these AIs, you want to be very, very careful about what the specified goal is and whether there's any technicalities so that you don't get any undesirable outcomes like this. The second thing to be conscious of is that obviously it's running through every one of these results, so it's rerunning our script again and again and again. So before you run Galapagos, you want to be very careful that you make the script as efficient as possible. So if there are display items that are taking a really long time, or booleans that are taking a really long time that aren't really necessary or something like that, I would suggest disabling it before you run the solver. You just want the bare bones script to test the outcomes so that it's as fast as possible. Now that we've got up to this point, you can see that these results pools are honing in on the best possible outcome. So this is a visual display of how effective all of these different results are. The other thing that you'll notice is that these results that are changing are very, very similar to each other. And this is because Galapagos doesn't just brute force every possible combinations of sliders. What it does is that it uses a genetic algorithm, so it's a type of evolutionary solver, to intelligently search for optimal solutions by mimicking natural selection. So for those of you that don't understand natural selection, what happens is this is a natural phenomenon that affects different species. So let's say that you start with an individual creature, so an animal, like for example a moth, which has a genetic code, and that genetic code will influence different factors about that species. So let's say what color it is. And then each time that that moth reproduces, it has slightly different genetic variations. So some might be slightly darker, some might be slightly lighter, for example. This was what was actually used in the original book, The Origin of Species, by Charles Darwin in, I think it was like the 1860s or something, where originally it was noticed that moths were a very light color so that they could fly onto birch trees and blend in to its surroundings so that predators couldn't see them very easily. And so the color of the moth affected the fitness value, so whether it was safe from predators and thus giving it more time or more lifespan to reproduce. So that's what we would refer to as its fitness value. But during the Industrial Revolution, when coal was burned, it was actually, there was so much pollution in the air that it actually made the trees and surfaces darken because of all the contaminants. So light-colored moths became more visible to predators and got eaten. And so they had shorter lifetimes to reproduce, whereas darker coloured moths became more camouflaged. And so this led to an increase in the proportion of dark coloured moths in polluted areas. This is really important because it's exactly the same way, or it's very similar to the way that Galapagos actually works inside of Grasshopper. So Galapagos starts with randomly generating a set of slider values, so that's our initial population. And then each combination of values is like an individual within that population. And each individual is tested by our script to produce a particular result. So that's our fitness number that we plugged in. So the fitness number which scores the results. And then the best performing individuals, so the best performing results, are selected to reproduce and poor performers are discarded. And so that's why we can see that this is quite, each one of these is quite similar as a result. And that's because it's honing in on the best value. So it's chosen this as the best possible outcome, and then it's testing very, very slight variations. Whereas when we originally started our script, you can see over here that it was testing a whole lot of different outcomes. Now it's much more honed in. And so it randomly changes each of these values slightly and to ensure diversity in the population that it's testing, and so that it doesn't get, I suppose, stuck on a single local optimum. And then each generation replaces the old one and the process repeats as it goes through and tries to hone out the best possible results. So over successive generations, as you let this run, Galapagos will hone in on better and better solutions. So the main thing you need to take away from this is that it doesn't test every possible combination. It uses performance feedback to, I suppose, intelligently explore the most promising areas of what's referred to as the solution space. So it doesn't just brute force everything. Now, what we can do here is that we can stop the resolver. And once we stop our resolver, you'll see that we've got a whole range of different results here, and it shows what the different outcomes are, and we can actually reinstate those different values if we wanted to. So we could test through a whole bunch of different values, or we could just take the most optimum one. But what I want to show you first is how we can start to create better outcomes. The first thing that I might mention is that we can test for multiple outcomes at once. So if, for example, we were also doing like area analysis or visibility analysis or solar analysis or structural analysis or something like that, imagine that our results were fed into this number slider and we had a result of something like 15,000 for whatever it may be. Maybe we're trying to optimize the area as well as the length. What we can do is that we could actually just add these two values together. So imagine that this is area analysis. This is length analysis. And then this is the number that we could test. So just hypothetically, imagine that I did like an area calculation and then plug that into here. I'm not going to go to the point of doing that, but I just want to explain the concept of how this could work. Then as it tests out these different numbers, it's going to take both things into consideration. So it's going to optimize for both area as well as optimizing for length. Galapagos is really simple in the way that it works because it's only optimizing this one number. And so if, for example, you wanted, and there are a few tweaks that we can make to this. So if, for example, you wanted length analysis to be less important than area analysis, what we could do to this number is that we could divide it. So we could divide it over here. take this number and we can divide it by 10. And then when you feed it into here, it's going to have 10 times less on the results. So because of that division, it's going to think that, or this area analysis number is going to have a much larger impact on the overall outcome. Because this number is now much, much smaller, it's going to have much less of an impact on our overall fitness. And so it's going to optimize for area a lot more than it's going to optimize for length. The other thing that I want to show you, so this is a pretty simple concept, but the other thing that I want to show you, if we get rid of all of this, is that I want to show you how we can start removing bad results. And what I mean by a bad result is that having something like this, which creates this really large area, is not actually the outcome that I wanted to get. So what's happening here is that these curves are self-intersecting like this. So what we can do is that we can use a curve analysis tool called curve self, like this. And what this does is that it will actually test these curves for where it intersects itself. So see here how this curve intersects itself over here. This is the test that we're going to run. So anytime that it intersects itself, we're going to say that this is a bad result. And the way that we're going to do this is that we can test whether there are any points in this list by saying list length. And you can see here that the result is 8. So because there are results here, we can say that this is a bad. So because there are points that self-intersect, we can tell that this is a bad result. So to test this, we can say equals. And what this does is test equality. And we can test whether this number equals 0. And you'll see that you will be fed a true or a false value. So basically we're asking, is this a bad result? Yes or no? And so at the moment, it's going to answer false. Or if we randomize it so that we get a good result, like this actually, where it doesn't self-intersect each other, then it's going to say true. So this is a good result, whereas before it was a bad result, so it said false. And how we can affect this numbered input is that we can use a component called pick and choose. So if we say pick and choose, which is this one here, what this allows us to do is that we can feed in this true or false value. And if it's false, it will take from stream 0. If it's true, it'll take from stream 1. And so what we can do here is that we can plug in our length output into stream 1, and then we can plug 0 into stream 0. And you'll see that the way that this works is that if you've got a good result like this, then it's going to say true, and it's going to feed in stream 1. Whereas if we randomize this so that we get a bad result, so if we randomize this to get a bad result like this, then we can see that it's saying false, and it's feeding in stream 0, which is feeding in the number 0. So I'm going to group this together. This will make more sense as we test it out. And I can call this remove bad results. This will make a lot more sense as we start to run through. So what I'm going to do is I'll just save our script, and then I'll double click here, and then I'll start running our solver. And what you'll see, if I make this a bit smaller, is that whenever we've got a good result that doesn't self-intersect itself, it will say true, and it will feed through the number itself. But if it's got a bad result, then it'll say false, and it will feed through that 0 number. And so every time that there's a result that intersects itself, it will make this number 0, and it'll tell Galapagos we've got a really bad output. And so now, just by feeding in this one fitness value, so just feeding in this one number, it'll understand what a good result is versus what a bad result is. And if we click on this display over here, it'll only display better geometries in the Rhino viewport. So this is just going to display our best result. So the result that's got like the longest pathway through our garden. And it'll start to hone in over time. Now, the other thing that I want to mention is that you'll notice that over here, there are two solver options that we can choose from. So one is called the evolutionary solver, and the other one is called a simulated anneal solver. So as I mentioned before, the genetic solver, which is the one that we're using at the moment, and it's got this pink icon, or the evolutionary solver, works by creating a population of random design options and then testing it all, and then keeping the best performers, and it will breed together the best performers to create new generations. So over time, these generations evolve to produce better and better results. So evolutionary solvers are especially good when you're working with complex problems that have many variables or unpredictable solution spaces, because it keeps multiple options in play and it can explore a really wide range of possibilities. Whereas this other option over here, which is called simulated anneal solving, is inspired by the physics of how metals cool and solidify. So instead of working with a whole population, it moves through one solution at a time, randomly making changes. So earlier in the process, it sometimes accepts worse solutions to avoid getting stuck in local traps, but as it cools down, it becomes more selective and starts to hone in on the best results. So the genetic solver is often better for like large, complex problems, while anneal solving can be much faster and more efficient for problems with smoother landscapes or fewer variables. So both are valid, and part of your job is to choose between which one of these would be most optimum depending on, I suppose, what you're trying to test. So this is a very, I suppose, simple example because I wanted to make it as understandable as possible, but there are heaps of other things that you might like to optimize. So you might, for example, like to optimize for solar loads or structural data analysis. So you might, for example, like to optimize for solar loads using Ladybug, or maybe you might like to use Karumba, which does structural analysis so that you could use that structural data as your fitness value to create the strongest structures possible. You might, for example, like to test for material usage, to use the smallest number of material components as possible, like in these concrete examples. Or maybe you might like to use visibility or floor area analysis, which can be really useful if, for example, you're designing apartment complexes or something like that, and you wanted to show it to the developer that, hey, we've actually done all this testing, and this is the single most optimum outcome possible. Now, I'm going to stop this resolver, and you can see that this has sort of broken our script, which is something that you need to be wary of. So what we could do is go back down and like reinstate some of these previous values if you wanted to. This is why it's really important to actually reinstate things. Because see, if we go back up to our top value, see it's actually broken our script. I think it's got something to do with the way that it's offset the curve. So you can go through and reinstate a different value, and you can actually choose through all of these different outcomes if you wanted to. The final thing that I'm going to mention is that if we go back to options, you've got a couple of different options here. So these affect things like population size, which is how many individuals are tested per generation, or maximum stagnation, which is like how many generations will take place without improvement before Galapagos stops, or even you can enable a runtime limit. This is really useful if, for example, your Grasshopper script runs for like 5 minutes. It's actually really difficult to hit stop resolver and the whole thing can crash, which is a massive pain in the ass. So if you wanted to, or if you've got a script that takes a while to run through, I'd highly suggest hitting enable and setting a maximum run duration. You can read through all of these explanatory notes if you wanted to create a really good understanding of Galapagos, but hopefully it's been really valuable to you to actually just understand how this sort of more generally works.
The next thing that we're going to cover is a really useful workflow to diagnose what may be wrong with the script. So this will usually take place where either somebody gives you a script and you try to apply it and it crashes, or where you've taken a script that you haven't run in a long period of time and you're applying it to a geometry or something like that it wasn't originally intended to use and it doesn't work.
Just so that we've got a script that's already sort of like working that we can work through, I'm actually just going to take this from my advanced fabrication course that you can see online. You don't need to follow through this and follow step by step and implement it yourself. You can just watch over for the next few minutes and observe the general workflow for fixing this script when it's crashing. But if you did want to check out this script, then it is available in the course's website. It's one of a number of lessons where I actually give you the scripts that show really, really advanced fabrication methodologies. And each one of these is designed as an exercise that you can take and you can fabricate these things in real life in a couple of hours. So just by printing these out on standard A4 or just standard printing paper and assembling them with some basic materials. For example, for this exercise, all you need is a printer and some tape. And I made this so that you can do these exercises and put them into your portfolio to demonstrate a really advanced fabrication understanding if you wanted to have the strongest portfolio possible to get into a university or job, because I can promise you that it will be really, really impressive to your architectural tutors or an interview panel if you're going for a parametric-based role. So all of these scripts are available on the course's website, but you absolutely don't have to use them if you just want to follow through and observe the learnings from this exercise for the next couple of minutes. Okay, so to give you a general idea of how this script works, it takes this initial geometry, which I've referenced in. This is just a sub-D that I've created, sort of inspired by Henry Moore sculptures. Just a general non-uniform, non-standardized geometry, which would ordinarily be very, very difficult to fabricate. And the way that the script works is that it breaks it up into panels, which we can see if we turn on the preview mesh edges like this. And maybe I'll pop it into shaded view so that it's easier to see. And then it triangulates all of these. So instead of being quads, it turns it into triangles. And then this part of the script here will take this mesh that we've referenced in over here, and it'll actually combine all of these panels together into strips, which are displayed here via the color that they actually are. So this is strip 58, and you can see that all of it is combined together. And each one of these individual panels is labeled either A, B, C, D, E, F, G, and so on. And the way that the script works is that it unrolls all of these into the individual strips that they are, and then it can be reassembled back together as a physical model. So it's a way of planarizing this particular geometry and then reassembling it together so that we can take it from being a really complex shape into being a real life model. There's heaps of these types of scripts that are available where what they do is that they just start off with a geometry like this. And so what you could do if you wanted to is create your own geometry, and you could reference those geometries in. I've actually done a process called internalizing the data here. So what you can do is that you could take this geometry and you can right click here and say internalize data, and you'll find that it will no longer link to this Rhino model. So if I wanted to, I could delete this out of the Rhino model and save this Grasshopper file, and you would no longer need to open the same Rhino file at the same time. It just means that you can share the Grasshopper script by itself and this entire thing will work. It's sort of like baking the geometry into Grasshopper. However, if I was to bake this out and make a few changes, so if I was to, for example, make it, let's say, 10 times larger. Yeah, so let's set this as our one geometry. And then I might change the number of panels. You'll see here that there are explanatory notes on each of these scripts about how to use them. So this here will set the number of panels that actually make up the mesh. If I wanted to, I could change this to be a much larger number, like 3000. And if I hit OK, you'll see that this script will take ages to run through ordinarily. So making small tweaks like that, like the number of panels or whether the size of the shape, will mean that this script doesn't run as smoothly as it originally does. It'll start crashing all the time. You've got two options when it starts crashing. Number one is that you let it run through. This could take anywhere between minutes or hours, or if, for example, you have grafted and flattened lists coming together and they're not meant to be, then it can end up taking multiple days and it's just not worth letting it run. Very annoying thing about Grasshopper is that once something starts running through, you can't cancel that, you can't stop it, and you can't uncrash it. And so what you end up having to do is just exit out of Rhino itself. And so if I say close window and press it again and again and again, eventually it will close. Or we can go to our task manager, and I can end the task. And I'm just going to start a completely new Rhino file. Now, often when Rhino crashes, it'll come up with a little pop-up saying that it saved an autosave file of Rhino. Inside of Rhino, if you go Properties, over here, you can change the autosave function. So at the moment, it autosaves every 20 minutes, whereas Grasshopper is completely different from this. Grasshopper, because it's such a small file size, will autosave every time you make a change to it, which is great news for us because it means if you go File and then Special Folders and then Autosave folder, which is this one here, then you'll see that it will actually create autosaves constantly for you. So every time you plug in a component or change a number slider, it will autosave that for you. Now, when I go to put this in, this is probably going to be an autosave version of the version that's crashed. So what I can do is I can right click and say lock resolver. What lock resolver does is that it means that the script will not run through. It'll let you look at the script. So see how it's added this little lock icon? So if I drag this over, you'll see that it's not actually computing this through. And so what I can do is that I can go over to our perspective and I can make some changes to this script before we start running it again. And what I'm actually going to do is I'm going to take the whole script, I'm going to select all of it like this, and then I'm going to right click and say disable. And what we're going to do is we're going to start enabling things in from side to side. And we can see that this larger geometry that I've made is referenced in still. And what I'm going to do is I'm going to make my way from the left-hand side over to the right-hand side and just start enabling things in slowly. If, for example, I enabled this and this was taking a really long time, I would know that this is the part of the script that's the issue. So when it was like 3,000 panels earlier, this would have been taking a lot longer, and you would know that you can't have this set to 3,000 panels. Just a note from earlier as well, see how I've got the time that each component takes to actually compute? This is referred to as the profiler, which, just to explain to you again, I can right click here and say, or I can click here and say canvas widgets and then turn on the profiler widget, and that's going to display how long each thing takes. And then I can start enabling things gradually one by one and see how long each one of them takes and whether there are any issues as we run our way through this script. You'll see there are explanatory notes through all of these scripts as well that sort of explain to you how each part of this works so that you can actually learn it yourself. So there probably aren't going to be any issues in this part of the script, so we just work our way through, enable it one after the next, runs very quickly. This is the part of the script that actually made all of those different colors. So we can enable all of that, and I don't think that there's going to be an issue there. Now, this part of the script, let's enable this. This is unrolling each of these panels and labeling them for fabrication. And we can see that this is taking a while. Now, the reason that this isn't working is because this was set up to create a plane or to create a surface that was 297 millimeters by 420 millimeters. And this particular size is referenced in so that, because it's the same size as a standard piece of paper that you would put into a printer. However, now that all of our pieces of geometry are much larger, you're going to see that they're much, much bigger than these pieces of paper. The pieces of paper are only the size of these green squares. And so what we might need to change is we might need to change the inputs of this from being A3 into A0, or else you're just not going to be able to print them out. A0 being one of the largest standard sheet sizes that you can print. So it's 841 millimeters by 1189, I believe. And we can replace these values. Again, see how I've accidentally plugged this into the wrong spot because I let go of my mouse. Ideally, you do not want to do this. This is why you would use the locked resolver when you start inputting things so that you don't have to wait 30 seconds each time this happens. So I'll let this run through. And then what I'm going to do, because I need to change two values at once, is I'll lock that resolver again. And I'll plug this into here, and I'll plug this into here. And then I can unlock that resolver so it'll start to compute things out again. And it's just going to save me the effort of actually having to disable and re-enable things again and again. So you can see that this is sort of mostly working. It's slightly too large for this panel. That won't fit on an A0 sheet, but it's running in 4 seconds because it does actually fit. Now the next thing is that we need to, let's enable these components here. And we can probably enable this. This creates the paneled labels for the text as we go through one by one. And there doesn't seem to be any issues with this. And so we can enable all of this part, which is what gives us our fabrication files. Now, when we look at these panels, you can see that the text is really, really small, like way smaller than it was originally to create that labeling. I'm just going to turn the preview of this off. And so what we can do is that we can look at these notes for where the text size is. So step 5 is this sets the size of the text, make it appropriate for your panel sizes. So instead of being 3, maybe we could set it to being 10. And now this is going to be more of an appropriate size for this. And so this is generally speaking how we will go through and fix up scripts that you have issues where it crashes again and again. So just to reiterate, our workflow is that we would check the autosave folder, we would lock the resolver, we would disable everything within this script, and then we would work our way from left to right, and we would just check each step. And the reason that we do this is because if there was an issue here, maybe it might be making like 10,000 mesh faces or something like that. If it's creating 10,000 mesh faces, it's going to be exponentially longer as we work through step by step. So that's why we disable it all and then work our way through from start into the finish.
I thought it would also be really useful to show you a whole bunch of different common issues that you might have whilst working inside of Grasshopper and how to fix them.
I'm just going to start by making a new document here. By far the most common issue is combining grafted data with flattened data. So you can see if, for example, we have a series component and it counts to 10. I make a panel to show this. These are all of the different results. You can see that there's 10 results here. If we were to multiply these, so multiply this and then this, you'll also see that there's 10 results, like so. So just squaring all of this. If we were to graft this and flatten this, then what's going to happen is that there's going to be an exponential number of results. So instead of having 10 results, it's going to have 100 results. This becomes an issue if you were to, for example, scale some geometries, or if you were to boolean something, whatever it may be, where you may be expecting 10 results, but it ends up making 100 results. So it ends up squaring the number of results. You need to be very careful of not plugging in grafted and flatted data together. You need to make sure that both of these data trees will actually match each other. And this is because if, for example, you're doing this with 100 pieces of geometry and you're scaling them, you're going to end up getting 10,000 results instead of 100 results. And it's going to completely crash your script. So be very, very careful to make sure that data aligns. That's the number one issue inside of Grasshopper. The second thing is that you should be aware, if we create a couple of squares here, like this, and maybe we can create a second set. So I'll reference these in here, and then I can hide them. Then I can reference these in to another geometry container. And if we use our Boolean tools, so solid union, like this, most of the time solid union will work. Or if we say solid difference, like this, we can take this, most of the time this will work, However, if you end up working with mesh geometry, so if we say mesh brep, we turn this into a mesh, and then we turn this into a mesh. We use mesh union. Plug in our meshes here, and we can delete solid union. And then we use mesh difference, and we can plug our mesh into here to replace this. And we can bake this out to take a look at it. You'll see that this hasn't quite worked. Unfortunately, Grasshopper's mesh union components just aren't quite up to scratch. Grasshopper uses all the same API or all the same code from Rhino, and Rhino's not great with mesh boolean. If you wanted to have a really reliable mesh unions, you'll need to use a specialized piece of software like Materialize Magic. Is something that I've found is really, really effective and really fast and never runs into issues even with like hundreds of thousands of meshes, whereas Rhino and Grasshopper are absolutely not like that. So to fix this, strongly suggest running it as a solid union or solid difference. It'll take a lot longer than mesh union or mesh difference, but unfortunately that's the reality that you need to work on. Now, the other thing to know about meshes is that a lot of the time you'll have a mesh that looks like it works, but when you plug in a panel, it will say invalid mesh. So this isn't an invalid mesh, but sometimes it'll break the mesh and it'll say invalid mesh. Or sometimes you'll go to bake some geometry in and it'll warn you that this is a broken mesh. The way that you can fix this is that you can use a component called rebuild mesh, which is this one here. And it'll give you a couple of options. All you need to do is plug it into this mesh input here if you've got a broken mesh, and then we can use boolean toggle and turn some of these onto true. So usually when you rebuild the normals, cull unused vertices, unify the normals, or like, you'll find that it will normally fix this mesh. Again, this doesn't say invalid mesh at the moment, but if you have it say invalid mesh, then this will fix that issue. The final thing I might mention is that over here, if we were to take our mesh geometry here, and I'll make another geometry container, you can see that all the data instantly flows through this from one container into another. If you've got a very long script that's got multiple parts, I would suggest using something called a data dam, which is this one here. And what it does is that it will stop the data actually running through this until you click this play button. If, for example, you were to start up a really complex script that had multiple parts to it, you might not want all of the parts to run. So you can use a data dam to stop it until you manually actually open or close this again. There's also a component called a recorder, data recorder. And what will happen is that each time you plug this in, it will actually save out whatever data goes into it. So you can see here that if I plug it in again, it's going to keep saving this out and doubling up. And what you can do is you can press this X component just to sort of get rid of it. The other thing that I might mention is that you don't have to manually set geometries like this. You can use this component called geometry pipeline, which is this one here, in which case you can set a layer. So at the moment I can take my default layer and I can call this default. And it will take any geometry that I've got on this default layer. So if I now type in show, and it shows all of these meshes, what I can do is I can specify the type of geometry I want. So I could double click this and have points come in, or curves, or surfaces. And then this last one is meshes. And so you can choose which type of geometry you actually want to come in. The thing that you need to know about this is that if you had a sublayer like this, so we'll call it layer 1, so default layer 1, and I move all of this geometry onto layer 1, obviously it's not going to come in. Then what I can do is that for the layer name, I can just put in 2 colons like this, and then call it layer 01, and now everything from that sublayer, so layer 01, will now come in. And it means that I can manually go and start creating more geometries like this. and anything that's within that same layer will be referenced in automatically rather than having to do it manually.
Incredible work getting through this entire tutorial series. I really hope that you're feeling a lot more confident with Grasshopper. I really hope that this has been a valuable resource. If it has, make sure that you, potentially, if you want to, consider supporting Legacy Design Studio and everything that we're trying to offer through either like buying a product, looking at the full modeling and visualization and rendering course that's available on our website or Patreon or whatever that may be. But either way, I'm really happy that you made it the whole way through and found it valuable. The last thing that I want to touch on is like where to go through here. The next things to do is to start practicing designing inside of Grasshopper. So thinking to yourself, like, if I was to make a particular type of geometry, how would I actually do it? How would I script it up? Getting a lot of practice in designing different types of geometries. There's a whole lot more that you can still learn. So learning the nuances of a whole bunch of the different plugins through the Food for Rhinos, I suppose, website. Downloading them, reading through what they're sort of about if you wanted to develop more specialization in that. You can learn to use this as a documentation tool, so using like Grasshopper inside of Revit and also Grasshopper inside of ArchiCAD, which are building information modeling softwares. And lastly, there is still quite a bit more that you can technically learn on data structures that I haven't introduced you to. So like really advanced notations and writing things out if you wanted to. And finally, you can also learn to code inside of Grasshopper, so coding with Python or C# or whatever scripting that you sort of want to. Python and C# are the main ones. Python's typically considered more easy to learn, is my understanding, but also C# can be a little bit more capable as a script or as a language if you wanted to implement it. And then you can also use all of these tools to actually code up your own plugins as well if you're ever interested in it. Either way, whatever you want to take from this and wherever you go to learn, I wish you the very best with your future endeavors with it.